Before I can finish my PNG decoder, I need to know the inflate algorithm. I've read the spec, but I'm still not confident, so I'm going to read Puff.c and Puff.h as well as the ReadMe from Madler's contribution to zlib. And this is an inflate algorithm that has been written in a simple way, so it's not optimized, it's just written to be understood for an example of how to do the inflate algorithm. First thing we're going to do, ReadMe. Puff, a simple inflate, the 3rd of March, 2003, Mark Adler, madler@alumni.caltech.edu. What this is. Puff.c provides the routine puff to decompress the deflate data format. It does so more slowly than zlib, but the code is about 1/5 the size of the inflate code in zlib and written to be very easy to read. Why I wrote this. Puff.c was written to document the deflate format unambiguously by virtue of being working C code. This is meant to supplement RFC 1951, which I've already read, which formally describes the deflate format. I have received many questions on details of the deflate format, and I hope reading this code will answer those questions. Puff.c is heavily commented with details of the deflate format, especially those little nooks and crannies of the format that might not be obvious from a specification. Puff.c may also be useful in applications where code size or memory usage is a very limited resource and speed is not as important. How to use it? Well, most likely, you should just be reading Puff.c and using zlib for actual applications, but if you must, include Puff.h in your code, which provides these prototypes. Which provides this prototype. Int puff unsigned char pointer dest pointer to destination pointer unsigned long pointer dest len amount of output space unsigned char pointer source pointer to source data pointer unsigned long pointer source len amount of input available. Then you can call puff to decompress a deflate stream that is in memory in its entirety at source to a sufficiently sized block of memory for the decompressed data at dest. Puff is the only external symbol in Puff.c. The only C library functions that Puff.c needs are setJump and longJump, which are used to simplify error checking in the code to improve readability. Puff.c does no memory allocation and uses less than 2 bytes of the stack. If destlen is not enough space for the uncompressed data, then inflate will return an error without writing more than destlen bytes. Note that this means that in order to decompress the deflate data successfully, you need to know the size of the uncompressed data ahead of time. If needed, Puff can determine the size of the uncompressed data with no output space. This is done by passing dest equal to unsigned char pointer cast 0. Then the initial value of pointer destlen is ignored and pointer destlen is set to the length of the uncompressed data. So if the size of the uncompressed data is not known, then 2 passes of puff can be used, first to determine the size, and second to do the actual inflation after allocating the appropriate memory. Not pretty, but it works. This is one of the reasons you should be using zlib. The deflate format is self-terminating. If the deflate stream does not end in pointer source len bytes, Puff will return an error without reading at or past end source. On return, pointer source len is updated to the amount of input data consumed, and pointer destlen is updated to the size of the uncompressed data. See the comments in Puff.c for the possible return codes for Puff. And that's the end of the ReadMe. Taking a look at Puff.h. Alright, there's a big comment on the top of Puff.h. Copyright Mark Adler 20 02 to 2013. All rights reserved, version 2.3, 21 January 2013. Just a disclaimer. We're not going to read all of that. It's not really important to understanding. Mark Adler, madler at alumni.caltech.edu. Okay, C Puff.c for purpose and usage. If not defined, nil, define nil, unsigned char pointer 0. I wonder where nil came from. Is that a C thing? Because I've only used it in Go. But I really do like to use nil instead of null. I guess I'm a hipster. Okay, we got int puff, unsigned char pointer dest, unsigned long pointer dest len, const unsigned char pointer source, unsigned long pointer source len, and we have comments for each of these. Dest, pointer to destination pointer. Dest len, amount of output space. Source, pointer to source data pointer. Source len, amount of input available. And that is the prototype for the puff function, which is the only external symbol for this library. Sometimes I call this a signature, though from reading up on it, I guess this isn't technically a function signature, though many people might refer to it as such. And that's the end of Puff.h. Puff.c. This is where most of the content is. We have a disclaimer again. Oh, actually, maybe not. Yeah, let's read this. Puff.c, copyright 2002-2013, Mark Adler. For conditions of distribution and use, see copyright notice in Puff.h, version 2.3, 21st January 2013. Puff.c is a simple inflate written to be an unambiguous way to specify the deflate format. It is not written for speed, but rather simplicity. As a side benefit, this code might actually be useful when small code is more important than speed, such as bootstrap application. For typical deflate data, zlib's inflate is about 4 times as fast as Puff. Zlib's inflate compiles to around 20K on my machine, whereas Puff.c compiles to around 4K on my machine, a PowerPC using GNUCC. If the faster decode function here is used, then Puff is only twice as slow as zlib's inflate. Scrolling down. All dynamically allocated memory comes from the stack. The stack required is less than 2 kilobytes, or 2K bytes, 2 kilobytes bytes. Should just read that as it is. All dynamically allocated memory comes from the stack. The stack required is less than 2K bytes. This code is compatible with 16-bit ints and assumes that longs are at least 32 bits. Puff.c uses the short data type, assumed to be 16 bits, for arrays in order to conserve memory. The code works whether integers are stored big endian or little endian. In the comments below are format notes that describe the inflate process and document some of the less obvious aspects of the format. This source code is meant to supplement RFC 1951, which formally describes the deflate format. http://www.zlib.org/rfc-deflate.html. Change history. 1.0, 10th of February 2002, first version. 1.117, February 2002, clarifications of some comments and notes. Update puff, dest, and source pointers on negative errors to facilitate debugging deflators. Remove longest from struct Huffman, not needed. Simplify offs index in construct. Add input size and checking using long jump to maintain easy readability. Use short data type for large arrays. Use pointers instead of long to specify source and destination sizes to avoid arbitrary 4 GB limits. Okay, next revision is 1.2, 17th of March 2002. Add faster version of decode, doubles speed, but leaves simple version for readability. Make sure invalid distances detected if pointers are 16 bits. Fix fixed codes table error. Fix fixed codes table error. Or fix... maybe that should have been fixed instead of fix. I don't know. Provide a scanning mode for determining size of uncompressed data. Okay, scrolling down to the next revision. 1.3, 20th of March, 2002. Go back to lengths for Puff parameters, Gaily. Add a Puff.h file for the interface. Add braces in Puff for else do, Gaily. Use indices instead of pointers for readability. 1.4, 31st of March, 2002. Simplify construct code set check. Fix some comments. Add fix L codes define. 1.5, 6th of April, 2002. Minor comment fixes. 1.6, 7th of August, 2002. Minor format changes. 1.7, 3 March, 2003. Added test code for distribution. Added zlib-like license. 1.8, 9 January 2004. Added some comments on no distance codes case. 1.9, 21 February 2008. Fix bug on 16-bit integer architectures. Poland. Catch missing end of block symbol error. 2.0, 25 July 2008. Add define to permit distance too far back. Add option in test code for Puff to write the data. Add option in test code to skip input bytes. Allow test code to read from piped stdin. 2.1, 4 April 2010. Avoid variable initialization for happier compilers. Avoid unsigned comparison for even happier compilers. I don't know what they mean by happy compilers. I should probably look that up. 2.2, 25 April 2010. Fix bug in variable initializations. Obenheimer. Add const where appropriate. Obenheimer. Split ifs and question marks for coverage testing. Break out test code to separate file. Move nil to Puff.h. Allow incomplete code only if single code length is 1. Add full code coverage test to make file. 2.3, 21st of January 2013. Check for invalid code lengths in dynamic blocks. Okay, so now let's get into the code. Line 82, include set jmp.h for set jump, long jump, and jump buff. Include Puff.h, prototype for Puff. Define local static for local function definitions. So anywhere that you see local, it's just a synonym for static, but it's kind of giving you what the intended use of the static keyword is in that location of the code. Okay, lines 87 to 89, we have a comment block. Maximums for allocation and loops. It is not useful to change these. They are fixed by the deflate format. Define max bits 15, maximum bits in a code. Max L codes 286, maximum number of literal length codes. Max D codes 30, maximum number of distance codes. Max codes is max codes plus max decodes. Sorry, I'm looking at defines right now. Maximum codes, lengths to read. And then our final define is fix L codes, 288, number of fixed literal/length codes. Okay, scrolling down. On line 97, input and output state. So we have a struct called state, and the members are as follows. We have the output state, which are variables out, outlen, and count, and we have the input state where the variables are in, inlen, incnt, bitbuff, and bitcnt. And then we have one more group of variables. It's not really a group, there's only one. It's the jump buffer, and it's called JMP underscore BUF. Oh no, that's the type, sorry. It's called ENV for environment. Okay, now we're actually going to read the struct state in its entirety. Struct state, open paren, or open curly brace. Output state, unsigned char pointer out, comment, output buffer. Unsigned long out len, comment, available space at out. Unsigned long out cnt, comment, bytes written to out so far. Input state, const unsigned char pointer in, comment, input buffer. Unsigned long in len, comment, available input at in. Unsigned long in cnt, comment, bytes read so far. CNT stands for count. Int bitbuff, comment, bit buffer. Int bitcnt, number of bits in bit buffer. Comment, input limit error return state for bits and decode. JMP underscore buff ENV, semicolon. Closing curly brace, semicolon. I did omit some semicolons from the members of that struct. If you know C, it should be obvious where I am omitting those semicolons. We have a block comment on top of the bits function, which I'm going to read. It spans lines 115 to 125. Return need bits from the input stream. This always leaves less than 8 bits in the buffer. Bits works properly for need equals 0. Format notes. Bits are stored in bytes from the least significant bit to most significant bit. Therefore, bits are dropped from the bottom of the bit buffer using shift right, and new bytes are appended to the top of the bit buffer using shift left. And from what I know, the spec said that it uses network byte order, which might be important to remember when you're looking at this. Okay, so the function starts on 126. Local int bits struct state pointer s, int need. So we have parameters s and need. S is a pointer to the state struct, and need is the number of bits you need. 127, open curly brace. I'm going to start reading the body of the function without going over line numbers for brevity. Long val, comment, bit accumulator can use up to 20 bits. Comment on the top of a block of code. Load at least need bits into val. Val equals s, not dot, but pointing to member of. I'm just going to say arrow because otherwise it's going to be a mouthful. So let me say this again. Load at least neat bits into val. Val equals s arrow bit buff, while s arrow bit count less than need. Within the while loop we have if s arrow incnt equals s arrow in len. Long jump. You know, I'm going to say member instead of arrow. Long jump s member env, comma 1, and there's a comment, out of input. So if the input count, if you're asking for, let's see, stat input count. So I'm trying to figure out why is in count, why is it equal and not a greater than? Count and length. S.bit count less than need. Plus equals 8. Huh. So equal is out of memory because equal is out of memory because it's a check done. What we say? It's a check done before we gather more bits. It's a check done before a bit count is incremented again, before we take the extra bits. So if in count equals inlen, right? We're at the end of the data, and right now we're about to take more data, but we're already at the end. That's why it's an equal and then not a greater than or equal to or a less than or equal to comparison. I just want to know why that's the comparison. Okay, so on line 135 we have val or equals long cast s member in within brackets s member in count plus plus, and then shifted to the left by s member bit count, and the comment is load 8 bits. So we're going to load 8 bits from, let's see, s.in, in count, yeah, we're going to load 8 bits from input is probably in is a byte array, most likely. And so we're going to get that byte, and then we're going to shift it over by the bit count. And then we're ORing it with whatever the current val is. Val equals s.bitbuff. Okay. So my question right now is I'm looking at this and I'm wondering if we ask for less than 8 bits or a non-multiple of a byte, how is that going to work? Because I see in count is always being incremented here. And if that's a byte index, then we're skipping over data. But obviously this code has been thoroughly tested, so I'm just not reading it correctly. So I don't know. I think I'm going to just try to read through this multiple times rather than stop here until I kind of like understand what's going on here. But I'm not sure what that, why it's like that. Okay, so s member bit count plus equals 8, and right, because we are 8, because right, there's 8 bits in a byte. Okay, and that makes sense. While S member bit count is less than the needed number of bits, then we keep on looping. That makes sense to me. Okay. So they are, when we're accumulating bits, we're going to round up. So if you need 1 bit, it's going to give you 8 bits, right? If you need 9 bits, it's going to give you 16. Right, that's what I think was confusing me. Because I'm like, why is it always shifting by a byte when you might not be getting, you know, increments in that size? So looking at that, okay, so val, we got that long cast, and we access from the input using incount to get the next unused byte. And we just... Though I'm a little bit confused at if we try to S member incount is a state variable, and since it's a state variable, like it's a member of the state object, what happens if we want to get bit? We want to get, say, we want to get, say, 1 bit, but then later we want to get 1 bit again. Oh, you know, okay, so it's not, bits is kind of a stream. It's not like ask for 1 bit at the beginning of the data stream and then later ask for 2 bits at the beginning of the data stream. It's a stateful command because we're trying to kind of like sample the binary in our data stream, and our data stream is stored as a buffer of bytes, but the actual deflate spec is manipulating binary, right? So it's manipulating individual bits, but the actual way that the data is stored in the memory is stored in bytes. Therefore, the whole need for this function. Okay, so now that I kind of see that it kind of rounds up to the nearest byte when you ask for bits. And so this value, when we're shifting, so on 135, the comment says load 8 bits, and it's going to shift by S member bit count. It's shifting that over, so why does it need to do a shift? So okay, so bit count here is, it's stateful, but it's always a multiple of, well, it's probably not always a multiple of 8. But I'm guessing when you consume bits off of this bit buffer that we're going to like decrement bit count, and when we ask for more bits with this bits function, we increment bit count by 8. And so this shift is making sure we always have a continuous stream of binary. And so let's say there are 9 bits in our buffer currently. So first val is equal to the bit buffer. So the next byte we get is getting tacked on into the most significant bit area. So if you have 9, let's say the bit buffer starts with 9 bits in it when we call this. Then on line 135, we're going to grab another byte and we're going to shift it over to the left by bit count. So that means that we're going to jump over the bits that are already in the buffer and add more bits at the most significant bit position. So we're tacking on the new bits into the MSB position, the most significant byte position, and I guess we're going to consume them from the least significant bit position is what I believe that was already in the text, but now that I kind of see, now that I've kind of digested that, I'm going to go back up and kind of like read that comment at the top again. Okay, so bits are stored in bytes from the least significant bit to the most significant bit. Okay, so bits are stored in bytes from the least significant bit to the most significant bit. Okay, correct. So if you want to chain bytes together, right, you want to, since we're basically, when we are reading the bits in the byte, we're basically going to be reading from right to left, right? We're going to be reading the byte. We read the bits in the byte right to left because we're going MSB, or we're going LSB on the right to least significant bit on the right, most significant bits on the left. So we're going to read the bits in the byte from the right to the left. So we're going to read it backwards. So if it was like, I think Hebrew, you read from right to left. So we're going to read all the individual binary bits in that byte from right to left. And therefore, when we have multiple bytes stacked together to say, and we want to string those all together and have the have a continuous gradient of binary information, we're going to have to stack those bytes in the same direction from right to left. Think of it like if each byte were a billboard written in Hebrew, and you are you want to like walk down the sidewalk and you want to continuously read all the words on every single billboard. Like maybe each billboard is a sentence or is a word in a larger sentence. Then you would want to be walking from right to left and scanning the words in each billboard to kind of like read the sentence that was there. I don't know if I made a good analogy there, but I understand it. So I'm going to just read the format notes one more time because I understand, and maybe make some notes as well. So I'm going to just make a note here. on, so this, we're going to read these bits like, so if these are the bytes, then, right, obviously there's more bits in a byte than this, but if we're reading it, each byte needs to be kind of stacked in this order, and then we read the binary like this, right? So this is MSB here, and this is LSB, and we're kind of like reading like this. And so this is kind of what is going on. Okay, so now that I've digested that, let's keep on reading through this. Oh god, did I close it? Okay, yeah, let's keep on reading through this. Okay, so load at least need bits into val. That's on 130. And when we load the bits, we're going to kind of like round up to the nearest multiple of 8 bits because the actual data is stored in bytes. So we're going to go down to line 139 now that we've kind of digested that. Line 139, drop need bits and update buffer, always 0 to 7 bits left. So there's always 0 to 7 bits left, so never 8 bits left, huh? Okay, not sure why that is immediately, but let's keep reading. 140, s member bitbuff equals integer cast, val, right shift by need, s member bit count minus equals need. So it makes sense that bit count is going to be decremented by the same amount that you shift. And it's a right shift, right? Because it's MSB, it's LSB, sorry, it's LSB to MSB with LSB on the right. And that is the oldest stuff. The oldest stuff is on the right side. And so we're shifting off the oldest stuff. So I'm going to make a little, I'm going to take this right here, and I'm going to just make a little note here that, you know, shifting off the oldest stuff, right? So, okay, so that makes sense. Now I get why we're shifting off the oldest stuff. But why by need bits? Well, I guess it's kind of, they talk a lot about a scrolling window, and so maybe I could use a scrolling window analogy here. I am guessing that the bit buffer is always, it's always full. Well, I mean, at the very beginning it's not full, but once it's full, it's always full, and you just drop off old stuff to make room for the new stuff. And that's why you're always shifting off by need bits, because you're just making an accommodation for the new bits that need to get put onto your buffer. Okay, and there's an integer cast. So val might actually have, might be a bigger type than int. Yeah, I'm gonna guess it's a long, right? So it's a long, it has more bits than int. Not always, depending on your operating system, though. I think sometimes int and long can be the same size, but there's a cast. Okay, yeah, I think that makes enough sense to me. Well, hold on. So val. Okay, so up here we don't have to drop the bits immediately before we're tacking on the new bits, because val is a long and has more space than the int. But before we reassign a val to the bit buff, right? Because we loaded the bit buff into val so we could work on it. Before we load val back into the bit buff, we're going to drop off the old bits. And so when you ask for more bits, if I ask for 5 more bits with this bits function, then the assumption, I think, is that if I ask for 5 more bits, it means that I've already used 5 bits. So asking for however many bits I ask for here, the code is kind of assuming that you have consumed need bits. So when you call this, it means I've consumed this number of bits, give me this many more bits. So that's kind of how I'm reading that. Let's keep on going through here. I know I am going slow. This isn't like a reading as normal, but it is code. So, I mean, if I were just to read it without taking the time to understand it, well, I wouldn't be adding any extra value to this, and I don't know, this is definitely not the same thing as reading a spec. Okay, so on line 143, return need bits, zeroing the bits above that. So let's see, return integer cast. We have value masked with a long, which is just set to the value of 1. We're going to shift it over by need bits, and then we're going to -1. Search zeroing the bits above that. Okay, got ya. So, because I tested this out in a calculator before, and why don't we do that to show you what's going on here. So, because when I looked at that first, I was like, what the hell? But, so if you take, so let's say we need 8 bits, right? So we start here, right? And then we're going to shift it over by, do we have a shift? Actually, no, let's just keep it here and just manually do it. So we start with that 1 long, and, oh, you can't see this, so let me move it over. Okay, so see if I can. So let's say we start with a 1 long right down here, right? Well, we're going to shift over by need bits. Let's say need bits is 8. So we're going to shift it 1, 2, 3, 4, 5, 6, 7, 8, right? And so now we're over here, right? And now, if we -1, what are we going to get, right? We're going to get all 1s in here, right? So if I go in to the calculator and I just go -1, 256 -1 equals, and now we have binary with all 1s here, and we get 255. So if you're super familiar with binary, then maybe that would make sense, but right, so now we just have all this, right? That makes sense, right? Because if we were to add 1 to this, then we would end up with this, right? All these would get reset, right? And you'd end up with a 1 here, right? And then if we want a -1, we'd end up here. And so if we start with a 1, we shift over need bits by 8, and then we -1, we get basically a bit mask that has 8 bits, which is what we need. Okay, so right here, we just know that this right here at the top is, hold on. We know that this right here is just creating a bit mask. And the bit mask is going to be this number of bits long, starting from the least significant bit going towards the most significant bit, right? And that's just to make sure that we don't have any junk data at the end of val. Or hold on. Return need bits. Oh, okay, got ya, because it's return need bits. Oh, okay, so this is how, this is the mechanism, because before I was kind of questioning, like, well, how do we get just a certain number of arbitrary bits when we are storing in bytes? And this is kind of the final answer to how we're doing that. We're just creating a bit mask of the correct length, and then we can bit mask off val to just get those specific bits. Okay, so after that function makes sense to me now. I am going to stop recording this because I think that took a long time to go through, and I think I'm going to go function by function from now on. So I just went over the bits function, and I'm going to go over the next function and hopefully be able to understand that as well. All right, we're going to go over the stored function. On lines 147 to 163, we have a comment, a block comment describing the function. Process a stored block. Format notes. After the 2-bit stored block type 00, the stored block length and stored bytes are byte aligned for fast copying. Therefore, any leftover bits in the byte that has the last bit of the type, as many as 7, are discarded. The value of the discarded bits are not defined and should not be checked against any expectation. The second inverted copy of the stored block length does not have to be checked, but it's probably a good idea to do so anyways. A stored block can have 0 length. This is sometimes used to byte align subsets of the compressed data for random access or partial recovery. Okay, so let's take a look. 164, we have local int stored, taking parameters struct, state, pointer, s. So I said parameters, but there's only one parameter. It takes the state object. So the stored function takes the state object. The local keyword there is a define for static. So that just means that the symbol isn't going to be exported. It's the way you do private in C code. On 165, we have open curly brace to start the function body. Line 166, unsigned len, semicolon, comment length of stored block. Line 168, comment discard leftover bits from current byte, assumes s arrow bit count less than 8. Or in other words, s member bit count less than 8. S member bit buff equals 0. S member bit count equals 0. That's lines 169 and 170. Line 172. Comment. Get length and check against its ones complement. 173. If S member in count plus 4 is greater than S member in len, return 2. Not enough input. So 2 is an error status for not enough input. Line 175, len equals S member in. Within brackets, we have S member in count plus plus. And that is a post incrementer, right? So the plus plus at the end. So that means we are going to fetch the value within this array. We're going to use the array access within count before we increment in count. Not really a fan of doing it that way, but I do see how it saves like a lot of extra typing and lines, but I don't know, it just feels like if it was written for clarity, then why did you do it that way? But I guess if you're like do that all the time, then it's clear to you. So clear is kind of relative. I would never put a incrementer inside of an array accessor like that. But that's the way they're doing it. So on line 71, len equals s member in with an array accessor, s member in count plus plus. Len or equal s member in with an array accessor, s member in count plus plus, and shifted over by 8 bits in a byte. Line 177, if s member in array accessor s member in count plus plus not equal to, what is that? Is that a bitwise, is that a bitwise not? So I don't know. So it's a tilde, len, and 0xff, or s member in array accessor, s member in array accessor, s member in count plus plus not equal to tilde len shifted over by 8 and masked with 0xff. So they are comparing the, it looks like some high order and low order section of a byte comparison. Well, no, it's a high order and low order byte of what? Len. Okay, so we're looking at the high order and low order bytes of the len variable there. But hold on. So tilde, what does tilde in C? Okay, so tilde in C is a bitwise not. So that's what I thought. That's what I thought it was, but I wasn't sure because like sometimes I see this and that's a bitwise not in some languages. So I got it all jumbled in my head. So I'm just gonna make a note there really quick. And we're gonna keep on reading. Okay, so let's look at this again. So lines 177 and 178, we're getting 2 bytes out of the input buffer, and then for some reason we are comparing them to these knotted values, which I don't quite understand why that is. So len yeah, so there must be some type of redundancy in the data that is allowing us to check one value in the data stream against another value in the data stream. And I see on line 179 we have a return true didn't match complement. So there's some type of complementary pattern. Okay, len. Okay, so we're taking 4 bytes in total. 2 bytes looks like it is, 2 of the bytes look like they are a redundancy. They're a complement, they're a binary complement, where all the bits have been kind of like inverted. And then we take 2 more bytes. So we're going to take the first 2 bytes and we're going to compare them against the next 2 bytes. And the first 2 bytes are the redundancy that's going to check the value of the bytes that come after. And we are going to just flip the bits in the redundancy by using bitwise not on len. And then since these are individual bytes, we have to, for the first byte, we just have to mask by 0xff, so that's on line 177. For the second byte of len, we have to first shift over to the right, and then we can mask by 0xff. And so there's probably something about in the spec about having some type of redundancy in the data, in the input buffer, but that seems like a lot of redundancy though, because we are saying int stored length of stored block is len. Oh, actually, it says len is the length of the stored block, so I guess it is the bytes that come after are the redundancy for checking. Yeah. Okay, so that makes sense, but I'm gonna guess maybe when we're saying we're trying to process a stored block that we are probably assuming, okay, let's see, at line 168, right, we're discarding leftover bits from current byte. So assume S member bit count is less than 8. So I'm going to guess that in the data there is some type of structure called a block that's like stored within the binary data, and that block must start off with like how long is the block, and then some type of and then a inverted number, an inverted bit value that is like a check digit, right? For the not a check digit, but it's like a check byte, right? So in this block structure in the binary, the first byte is, or the first 2 bytes is going to tell us the length, and the next 2 bytes after that is just a ones complement check on the previous byte. Okay, so I get that enough. Okay, so let's keep going. Okay, so copy len bytes from in to out. Okay, so that block structure tells you what the length of it is, and then we know that the next bytes are going to be data. So S member in count plus len greater than S member in len, return to not enough input. So the input count plus length, yeah, if the input count plus length is greater than the buffer's input length, then yeah, we wouldn't be able to get any so in len and in count for a second here. I thought in count was the length of in len. No, that can't be, because in len is, so okay, there's a buffer called in. In len is the total size of that buffer. S member in count must be the total number of bits that were read so far. And then we're going to add len to get kind of like the seek position within that buffer. And if that seek position is greater than S member in len, then we have seeked too far. We have done like a buffer overflow. We've seeked past the end of the data, the end of the input data, and that's why we're returning a 2 for the input. Okay. Line 184, S member out not equal to nil. So, right, we have to actually have a output buffer. And if we don't have an output buffer, if s member out count plus len greater than s out len, oh, sorry, if we do have an output buffer, then we're going to do a similar out of bounds check to see if we seeked past the end of the output buffer. And if that is the case, we're going to return 1 for not enough output space. Then we have a while len minus minus. So we're going to keep on decrementing len. And this is only in the case that we have an output buffer. So if we have an output buffer, we're going to keep on de-incrementing len until we get to 0. So that's as far as I'm concerned, that's a hackish way for like a it's a hackish way to do something that might be more clear, like a for loop. But let's look at the statement. So s member out within the array accessor, s member out count plus plus equals s member in s, and then in an array accessor we have s member in count plus plus. So we're just lining up the output with the input, right? We're copying in to out. And copy len bytes from in to out. Well, that's what it says in the comment on line 181. Is there anything else I'm missing here? Out count, in count. Yeah, so out count and in count right now are kind of being used as a seek position, right? So out count and in count will first start at 0, right? When there's nothing in, out, or in, or when there's nothing in the output buffer, right? Out count will be 0. And so you can use out count and in count as a seek position within the respective arrays or the respective buffers. So in count can also be thought of as, rather than just thinking of in count as a total, you can think of in count as a seek position within the in buffer. And out count, rather than thinking of that just as a total, you can think of out count as a seek position within the output buffer. Okay, and that makes more sense when you can think of it as that as well. There's almost like a candlestick problem here. If you're familiar with psychology, I think if you just Google candlestick problem, let's Google that for a second. Candlestick problem. Candlestick problem, Wikipedia. So there it's called candle problem. I'm not going to go into it, but the fact that I need to, on line 188, that I need to think of out count as both a seek position and as a tally makes me think of the candlestick problem. But now that I know that, we have an else, and that else is applied to line 184. So if there is not a buffer, then we're just scanning. There's a comment on line 190. S member out count plus equals len, S member in count plus equals len, right? So we don't have to go byte per byte because we're just scanning, and we don't need to increment as slowly. We can just go plus equal. Okay, and done with valid stored block 195, 196 return 0. So I think I got the general idea that the part that confused me is the check right here. Like I get that there's a check, but that means that I'm probably not aware that there's some type of data structure here that that I need to be more aware of. Um, yeah, yeah, okay, yeah. So I see this is not, when you're looking at this, it's not quite like a one-to-one copy from in to out, because we are going to kind of skip over, I guess, the header, if you will. So the bytes that specify metadata about the information, and the metadata in this case is the length of the data, those bytes we are skipping over. And these bytes are not actually going to be put into those bytes aren't going to be put into the output buffer, right? We skip over those, right? Because we're skipping over them right here. Okay, so I think now I understand the stored function. What I don't understand is that I understand there's some type of underlying data format encoded in the bytes or in the binary of the bytes. It's probably something that I read in the spec that I just didn't remember because there was a lot of stuff, and most of it I probably did not retain, honestly. But yeah, so that's the stored function. I think I have a good handle on this, so I'm going to stop recording, and we're going to get to the next function of Puff.c, and we're just going to keep on reading it until we understand it, and then we'll move on to the next function, etc. All right, the Huffman struct, or the Huffman state, whatever you want to call it. On line 206 to 209 is the struct. Struct Huffman, open curly brace, short pointer count, comment number of symbols of each length, short pointer symbol, comment canonically ordered symbols. So I believe they're talking about canonical Huffman codes. And you use canonical Huffman codes so that you can deterministically reconstruct the same Huffman tree by just looking at a frequency table of symbols. Because there's more than one way to let's say we had symbols A and B with an equal frequency. Well, is A going to be assigned to 1, or is it B that's going to be assigned to 1? And then, right, like which symbol is going to get a 1 and which symbol is going to get a 0, right? If they both have identical frequencies and there's only 2 symbols in your data, A or B, then how do you construct that tree? Is A on the left, or is it on the right of that tree? And in order to solve a problem like that, we use what's known as canonical Huffman codes, and that will make it so we can rebuild the Huffman tree just from the frequency information of the different symbols and always get the same tree. And that's important because then we can very compactly encode our Huffman tree into the data by just having a frequency table. Okay, let's read the comment on 199 to 205. Huffman code decoding tables. Count 1 ... max bits, so that's 1 to max bits, I believe inclusive, is the number of symbols of each length, which for a canonical code are stepped through in order. Symbol are the symbol values in canonical order, where the number of entries is the sum of the counts in count. Decoding process can be seen in the function decode below. Okay, so that is the Huffman struct, and we're going to get on to the decode function next. All right, first is the comment for the decode function on lines 211 to 233. Decode a code from the stream S using Huffman table H. Return the symbol or a negative value if there is an error. If all of the lengths are 0, i.e. an empty code, or if the code is incomplete and an invalid code is received, then -10 is returned after reading max bits. Format notes. The codes are stored in the compressed data. The codes as stored in the compressed data are bit reversed relative to a simple integer ordering of codes of the same lengths. Hence below, the bits are pulled from the compressed data one at a time and used to build the code value reversed from what is in the stream in order to permit simple integer comparisons for decoding. A table-based decoding scheme, as used in zlib, does not need to do this reversal. The first code for the shortest length is all zeros. Subsequent codes of the same length are simply integer increments of the previous code. When moving up a length, a 0 bit is appended to the code. For a complete code, the last code of the longest length will be all ones. Incomplete codes are handled by this decoder since they are permitted in the deflate format. See the format notes for fixed and dynamic. And fixed is a function and dynamic as well as a function. On line 234, we have if-def slow. So this is the slow version of the decode function, which should be the easier to read version of the decode function. I'm sure it's going to be a little bit difficult, but we'll figure it out. Line 235, local int decode parameter struct state pointer s and parameter const struct Huffman pointer h. So let me say that again because I didn't really make much sense. We have int decode and it takes parameters s and h. S is a state struct and h is a Huffman struct. Said verbatim 235 local int decode open paren struct state pointer s comma const struct Huffman pointer h close paren. Line 236 opens up the function with a opening curly brace. Lines 237 to 241 we have a declaration of some variables. Int len, current number of bits in code. Int code, len bits being decoded. Int first, first code of length len. Int count, number of codes of length len. Int index, index of first code of length len in symbol table. Okay, so that's len, code, first, count, and index, and they are all ints. Let's just keep going. Okay, within the function we have, oh, this is not within the function. This is, well, I mean, it's still within the function, but this brace right here, that's not the end of the function. That is part of a for loop. All right, so 243, code equals first equals index equals 0. So we're just setting everything to 0. We're setting code first and index to 0 succinctly with a one-liner rather than using up 3 lines. That's one of the things where I'm like, is that simple or... so I think their definition of simple is not doing anything clever. And it's not about avoiding doing things compactly, I'm guessing. Also, you know, I don't know, whatever, let's not rant. 243, we're setting code first and index to 0. 244, for len equals 1, len less than or equal to max bits, len plus plus, opening up the for loop with a opening curly brace. Within the body of the for loop, we have code or equals bits s comma 1, get next bit, okay. 246, count equals h member count with an array accessor using the value len. Does that make sense? Because len is iterating over max bits, yet well, this is the Huffman struct we are in on 246. Count equals h member count, and then array accessor using len. So okay, so it's the frequency table for the number of codes of a certain length. So the count is, yeah, count. So count could, I've done this before, but count right here would make more sense if it was called frequency, because this is a histogram. This is a histogram right here. It's a histogram table. It's a histogram table. We're going to look for the frequency value of length within the histogram. So the count that is the code length of count. Well, that might not be correct. This could just be the symbol count, right? So the symbol that shows up this number of times in our histogram. All right, let's just keep reading. So on 247, if code minus count is less than first. If length len, return symbol, return h member symbol, and then we have index plus code minus first. Else update for next length. So we'll do index plus equals count. Okay, yeah, I see. I wish they would put curly braces, like the whole like connecting, right? So this is, imagine that there's a curly brace like right over here somewhere, and then there's another curly brace like right after here somewhere, because this statement is only connected to this if, which I hate code written that way, but whatever. So this isn't going to get executed. This is like the else. It's like, I don't get the idea of why put the else in a comment when, whatever. Okay, so index plus equals count, first plus equals count, code. Okay, index plus equals count, first plus equals count, first shifted over to the left equals 1, code shifted over to the left equals 1. So that's a, you're going to first shift over, so you're going to shift over first to the left by 1, and then you're going to add a 1 bit. And you're going to shift code over by 1, and then you're going to add a 1 bit. This kind of looks like we're probably building canonical Huffman codes here. What was the function name again? Decode. So probably not if it's called decode. So let's keep on looking at this. So len, number of bits, code, len bits being decoded, first code of length len, count, number of codes of length len. So this is the one I want to really pay attention to right now. Count, number of codes of length len. Okay, yeah, so that's definitely a histogram. Yeah, so 246. This is definitely accessing a histogram, and but it's not a histogram of different symbols. It's a histogram of how many symbols of a certain length do we have, or how many symbols of a certain frequency do we have. So it's kind of like a meta. It's kind of like a meta histogram. It's a histogram of a histogram, kind of. Yeah, yeah, yeah. It kind of is a histogram of a histogram. Because whatever we're gonna fetch out of here, it's not a symbol. It's how many symbols of that length do we have, and we'll store that in count. Okay, so I get the intention of line 246 now. As far as building the code on line 245, and where are we using code? We're using it down here. I'll be back. I'm gonna read this some more, but I'll be back. Alright, so I'm still looking at the decode function. What I'm kind of confused about is decode, what is it decoding? Because I guess initially I was thinking, oh, it's gonna decode all of the data. But that doesn't make sense. Because there's no input and output buffer. Input and output buffer are not referenced here, so that's not what it's doing. So what exactly is it decoding? So we have the state struct and we have the Huffman struct, and I believe the Huffman struct is just what we're going to use as the necessary key to help us interpret whatever is inside of state. I was going to read over this again. Len, current number of bits in code len, bits being decoded. First code of length len, count number of codes of length len, index of first code of length len in symbol table. So maybe it's decoding a symbol table. So code first index equals 0, so reset everything to 0. And then we're just going to loop through len equals 1. Len is less than or equal to max bits, len plus plus. Okay. So the first thing I notice is this does not return anything. This function it returns an integer, and that's for a error status. But otherwise, it has to communicate what it's done by putting the value somewhere. Oh, so I see return. Okay, so it does return a symbol, but if the symbol is negative, it's an error code. Local int, yeah, okay. So code or equals, and it's gonna get a bit. So this is how it's getting into the state. So it is getting things from the input buffer, but indirectly through the bits function. Okay, so we're gonna get 1 bit, and we're gonna OR it onto code. Code starts out at 0. So there must be a shift somewhere. Oh, yep, at 252 we have code shifted over 1, and then we add a 1. So it's interesting that we're appending a 1 at the end to the code rather than appending a 0. So that must be of some significance. In some cases it won't matter, because later at 245, when we hit 245 again, we do code or equals and we overwrite it. But I definitely think there is some significance to shifting over and appending a 1 rather than 0 filling. Okay, so 245 code or equals bits s comma 1. 246 count equals Huffman member count accessor length. Okay, so we're going to look at the code that is the current amount of bits long. Okay. And okay, and so it looks like so it looks like we're seeking through the input buffer using line 245 and gathering more and more bits. And every time we gather one more bit, we're trying to see if that code exists in the Huffman table. And we don't do anything else with the code. So after 252 here, we don't do anything else with the code unless we loop back up to the top. So this bit is definitely getting overwritten, so I'm pretty sure that could be a 0 or a 1. It doesn't matter. So I'm not sure why the 1. That seems it could just be a different way to write code equals code shift. It could just be a different way to. So I'm thinking that this is confusing because it could also be this, and it would do the same thing. In the end result would be the same thing, right? Because it's going to get overwritten here. But I think what they're doing is they're just trying to write this. Code equals code, and then shift 1 like that. So they're just trying to bit shift it over 1. So this is going to bit shift over 1. And then they're tacking on a 1, right? But this is equivalent to this, though. That's why I'm not sure. But then when you look at the code, though, the only other place you're going to use this is up here, and you're immediately overwriting it. So I have no clue why they did that. This seems more clever than it needs to be. But okay, but the general idea is that we're collecting more and more bits and building up a larger and larger sequence of bits. And each time we tack on one more bit, we're going to see if it is Huffman code. Okay, so with knowing that, so count equals count len, right? So we get the we get the number of bits in the current code, and we get out the frequency. Count number of codes of length len. Okay, so let's say the code is 1100, right? And so the current code here is 1100, so that is a length of 4. And maybe we have 1100 in here, and we also have 1101, right? So we have those two codes. So count would return 2, because there's two different. So there's two possible codes that it could be. So as long as this count is non-zero, then we need to do some type of comparison against each one of those codes. So code minus count. Now, why is it code minus count, though? So first is probably the first. Okay, first code of length len. Okay, yeah. So first code of length len. So the binary because they're canonical Huffman codes, every subsequent Huffman code of a certain length is a larger integer value. Okay, that kind of makes sense. But why code minus count? Now, the reason why I'm confused here is because code is it's like a binary sequence, and then count is the number of bits in that sequence. And I don't understand how you can take I don't understand how you can take this and minus that and have some type of meaningful comparison. What's my timer doing? God damn it. I don't even know what that timer was for. So yeah, I don't understand this comparison. If length len returns symbol. If length len returns symbol, if length len, like as in length equals len, well, it can't be that, because if that was the case, wouldn't you just have length equals len? Which wouldn't make... Yeah, I'm not sure. I'm gonna stop recording for a second and try to like do some bit shifting and kind of like understand this. Okay, I get it. So let's say we have two codes of length 7. So this code and this code. Or sorry, this code and this code and this code. They both share a common prefix. And then actually this is bad because we can... Technically there would be 3 of these, I believe. Right, we could have... So we could also have this, right? So there could also be 3. So let's say there's 3 of them. So let's say there's these 3 codes, right? And they all share this prefix. And then you just count up, right? You count sequentially. That's the whole thing that makes canonical codes kind of like standardized, is you have some type of common prefix. And then for all codes of this length, we're just going to count up like this, right? So this is 1, this is 2, this is 3. Okay, so if we're here and we minus 3, right? So code minus count less than first. So this is the first code. And if we're here and we minus 1, minus 2, and if we minus 3, we're going to be over here somewhere, right? So it'll be less than first because this is first. And so we're saying that if we're over here, then the code must exist, right? Because if we were... if our code was something greater than this, so like 1, 1, 0, 1, 0, 0, you know, we minus 1, 2, and 3, and this is the first code, and this is now equal to first, but it's not less than first. So this code is not part of our group of Huffman codes. So that's kind of like why this comparison is like that. The thing that confused me is I'm like, well, there's a lot of combinations that are less than first. The trick here that I was omitting is that when we're going through this loop, right, it's gonna do this comparison on the smaller sized codes first, right? Because we're building up. So if we tried to do this logic, like if we try to go backwards through this loop somehow, like if we try to build a loop where we somehow start with all the bits and then we take off bits and we go from a greater length all the way down to length equals 1 backwards, then this formula here would be invalid. It's kind of like if like hold on. Else it's kind of like how this right here would not be the same as right. That this oh sorry, it's kind of like how this is not the same as this, because of well, I don't know, that might not be the best way to explain it, but I get it, but I just need to explain it a little bit better. I don't know if I need to explain it better. That this is the best way to detect if the code is part of, if the current code is part of the sequence of codes of the current length. And in order to make this comparison, we need to know what first is. So what is first? So first, where are we getting first? So first looks like it might be being built on the fly. But yeah, that's an important thing. So we have first plus equals count. Okay, so that really doesn't make much sense to me. So I might have to look at how Huffman codes are built again. So, like, what determines what this first code is? And I don't know. So I did like so let's look. I have some code that like builds Huffman codes here. And if we take a look at that, I'm going to take a look at that. So you notice that BL counts 7. So the codes of length 7, there are 6 of them. And when we generate our canonical Huffman codes, we can see that the number are 6 codes of length 7. The first code looks like this, right? And then if we sequentially add numbers to this, so 1, 2, 3, 4, 5, and then 6. Okay, yeah, that makes sense. Because on the seventh, does that make sense? So this is the first one. The second one, we're going to set this bit. So hold on, let's just take this for a second. So this value right here, let me just take this. Okay, so let's say we have the code of length 7, and there's six codes of length 7. So if we're doing this, 6 codes of length 7, and this is the first code here. And this 8 here, in our source code, 1 code of length 8. So let's go back to our notes. One code of length 8. Okay, so if we take this and let's look at what the other codes are, because we said we have 6 of them. So 1, 2, 3, 4, 5, 6. So we're going to add 1 like that, then carry, then 1, 1, and then there'll be a 1 here. And then this would be a 1 and a 1 like that. Well, that isn't quite right now, is it? Oh, wait, hold on. The next code, there's a 0 here. Well, you notice there's 1 more bit. So, bam, move it over like that. And now, of course, this is much... Okay, now that's starting to make much more sense. Because if the next code has 1 more bit, then... Okay, okay, that's starting to make a little bit more sense. Hold on. Just making a note of the making a note of how I got that. Okay. Okay, so I definitely get how that's working. So the next part is this lookup here. So symbol index code minus first. So we have an index. Where is this index coming from? Index is going plus equals count. First plus equal count. Okay, so index, right? So index can jump over however many symbols there are of that length. First plus equal count. So the first symbol is somehow so the first Huffman code, I guess, is... So this first, like how they're generating the first seems kind of weird. They're just saying that it's the count of We're just appending counts, and that gets us the first, really? Yeah, I'm not sure how that is. Okay, so generating the index, okay, that makes sense, but generating first, oh wait, okay, so first plus equals count, and then there's this shift being applied to count. So I believe that is somehow the same as this algorithm here. So this would be count. This would be count. And the code is code plus count. So this would be, code here would be first. And first plus the number of symbols of this many bits long, and then shifted over 1, and that is the algorithm to get the next Huffman code. So I think I need to understand that algorithm a little bit more, but this algorithm right here is actually what I am looking at on this, and then that is the same algorithm, because we're taking the Huffman code, adding the count for the next Huffman code after that, I think. Yeah, I'm pretty sure that's what's going on. And it says else update for next length, right? So it's getting the next first code. So it's kind of like generating the it's not storing a lookup table anywhere for the first code. I feel like it might be a little bit more straightforward if it stored not this. If it kind of like stored this table instead of generating it on the fly, I think it might be a little bit more straightforward. But that's basically what it's doing. It's generating this kind of table. All these are the firsts. All these binary sequences you're seeing, they're the first Huffman code of a given code length based on a frequency table. And if we look at our frequency table, right, here's our frequency table. And but yeah, they're generating that table of canonical Huffman codes on the fly, and that's kind of what I was confused about. Okay, so with that, so I do kind of know like where first is coming from and how they're getting it. I don't quite understand well, if you shift everything over, let's look at the results here. So shifting everything over, Okay, so we add the current code, the current first code, plus the number of codes there are, right, to make sure that none of those bits get used. And then we just shift everything over to the left one. And then okay, that kind of makes sense. So if we take the code and then we increment, we're gonna reserve certain binary sequences that end in the termination of our you have to make sure that the Huffman code, a Huffman code cannot be a subsequence of a shorter Huffman code cannot be a subsequence of a longer Huffman code. And in order to make sure that doesn't happen, we're going to take the current code that has some type of binary value, and then we're going to add BL count bits, right? So if, think of it as, so this right here, let's take a look at that. So right here, you have something like this. And let's say your code is this, right? And let's say you have 3 codes, right? So you have that code, and then you have this code, 1, and then 2. I guess, did I say 3? Well, let's do 4, just for the sake of it. So let's say you have codes of length 4, and you have 1, 2, 3, and 4 of them, right? And so bits minus 1, right? Because there are oh, that's the previous code. Okay, so the previous code, okay, got you. So let's say the previous code is okay, so let's say that this is our previous code. And let's say this is our previous code, BL count bits minus 1. And then the next code, there's 3 of them. So 1, 2, 3, right? Because we're going to add code to it. And so so this plus 1, 2, 3. This is our last code of this group of codes. And then we need to shift that all over by 1. And so that will give us right, that'll give us just a, right, we're just going to tack on something like that. And this right here cannot be found in here, right? This is not a subsequence of any of these codes. Is that always the case? Yeah, that makes sense that it would always be the case, right? Because if we have this and we're adding to it, oh, sorry. Oh, God, you can't even see that. Okay, so let's say this is our previous code. So this is BL count bits minus 1. This is a previous code. Our next code has 3 codes of length 5. So the first thing we're going to do, so this is our code of length 4. And let's say we only have 1 code of length 4. And that's looked up by getting this, right? Bits minus 1. So the next code is length 5, and it has 3 of them. So first thing we do is we add code to the previous code. So the code length, the number of codes Or hold on. No, I'm not sure if that's right. But I kind of get that if you take this code, right, and then you add the... If you take a code and then you add the number of... how many codes are of length 4, right? Let's just say there's, like, 3 codes of length 4. So 1, 2, 3, right? We're just adding 1, add 2, add 3, right? Because there's the code length. Then this will never collide with any of these, right? Because you're never gonna get the original value if you just keep on adding to it, right? This plus whatever will never equal this, right? And so we know that these, if we add to them, they're not going to collide. And then we're going to shift it over, right? So now we have this, and we know that these are never going to these are never going to have this as a subsequence because we added first, and then we zero fill. I kind of get it. I don't get it completely. So I kind of get it to where, if we go back to the code here, so code minus first, index plus code minus first. So really, I want to know what the hell this is doing. So the first thing is there's some type of symbol table, and we have the index into that symbol table. Now, what I don't get is why we have code minus first. Okay. Oh, yeah, because they're sequential. Oh, got you. Because they're sequential, right? So if our Huffman codes look like this, and they're all sequential, then let's say we have, these are our codes. So let's say these are our codes, right? So code minus first. So this is first. And then we add, this is plus 1. Our second code. Our third code, plus 2. Plus 3, right? So this is the binary. This is the first code, Huffman code in binary. The second one, the third one, the fourth one, right? And we just add 1 to it to get the next one. Therefore, if code minus first, let's do something really easy. Code minus first, well, if this is first, and it's also the code, right? So code is this, but it's also first, then that's 0 minus 0, and that's index plus 0, right? Now, if we have this, right? Well, first is the smallest. First is always going to be smaller, right? So that's why smaller is on this side, right? So we don't go negative. So this minus that is 1, right? This minus that is 2. This minus that is 3, etc. So we get the correct offset, right? By doing that. Okay, so that makes sense now. And then we just start at index, and we just add that, right? Because this index is going to be the index of the first Huffman code, and that's how we're going to get it out of the symbol table. Okay. So that makes sense to me now. So looking at that, I kind of get this whole function now makes sense. Now, am I going to remember? I feel like I'm not going to remember that, or I'm going to have to like go through this a few more times. But I think that the decode function, I think I've looked at it enough to where I get what's going on. I get that I get how we're going to retrieve this symbol. Now the next thing is the input. Okay, so the input is just indirectly looking at the input buffer. So input, indirectly we're going to look at the input buffer by siphoning bits off of it using the bits function. And then once we get a positive match, we'll just look it up like this and return it. So our input is right here, and then our output is right here, basically. And then everything else is kind of a whole bunch of transformations in between. Yep. So we're gonna seek through the binary input by collecting one bit at a time, and every time we collect another bit, we do some crazy stuff to figure out if we have a matching Huffman code, and if we have a matching Huffman code, then we look up the correct symbol for that code. So the symbol could be like, I believe would be just a byte, because we're using Huffman codes to compress bytes. So it's not just ASCII, right? Because ASCII is only 7 bits and there's 8 bits in a byte. So this isn't text compression, this is byte compression. A lot of times you're going to see the word string mentioned in either this code we're reading or in other parts of the deflate spec. But when they're talking about strings, they're actually just talking about bytes. They're not talking about ASCII, so don't get that confused. But yeah, so I get enough of that this makes sense. I feel like when I'll definitely use this to like write my own code, but I'm definitely gonna add more comments to how this actually works. But yeah, I'm satisfied that I now understand the slow version of decode. We're also going to look at the fast version next, and if I don't understand the fast version, I think I'm just not going to try to understand it, because I just need to understand, one of them. And I believe if it's the fast version, there's a chance that it is more clever, like harder to read and harder to understand. And I really just want enough knowledge to understand the problem and code a solution. I'm not going to worry about optimizing yet. Looking at the fast version of decode, comment on 258 to 260, or more like 257 to 261. A faster version of decode for real applications of this code. It's not as readable, but it makes Puff twice as fast, and it only makes the code a few % larger. Okay, so let's take a look at this and see kind of what the differences are. 263, local int decode, struct state, pointer s, const struct pointer Huffman. Sorry, I said that totally wrong. Let's read it verbatim first. Local int decode open paren struct state pointer s, comma, const struct Huffman pointer h, close paren. So it's a function decode, takes the parameters state and Huffman, or in other words, it takes the parameters s and h, which are a state object and a Huffman object, respectively. On line 264, we open up the function, and we declare some variables on lines 265 and 2 to 272. So 265 to 272, we have variables length code, first, count, index, bit buff, left, and short pointer next. Everything else is an int except for short pointer next. So len, current number of bits in code, len bits being decoded. First code of length len, count, number of codes of length len. Index of first code of length len in symbol table. Bit buff, bits from stream. Left, bits left in next or left to process. Left, bits left in next or left to process. Okay, short pointer next number of codes. Okay, let's take a look. Or not, if we scroll like that. What the hell? Okay. So, line 274, bit buff equals s member bit buff. Left equals s member bit count. Code equals first equals index equals 0. Okay. So setting everything to 0. Len equals 1. Next equals Huffman member count plus 1. While 1, so we got an infinite loop here. While left minus minus. And then code or equals bit buff and 1, so we're going to mask. We're looking at the bit buffer, and we are taking the first. We're taking the first bit in the bit buffer, right? Because we're going from least significant to most significant in that bit buffer, and we're appending it to the current code. So we're building up the code again, but it looks like instead of using the bits function, we're actually going to use the bit buffer. And that's what's going to make this faster, because we're not going to have a whole bunch of function calls. So we're going to take the bit buffer, and we shift it over to the right, and oh, okay, I was totally reading this wrong. It's not shift over 1 and then append to 1. That's just it's bit shifting over, it's bit shifting it over by 1. It's not, yeah, okay. When I was reading the code earlier in the previous function, I was not interpreting that operator correctly. Yeah, it's definitely it's not shift and then or a 1 on. That wouldn't even make any sense. So this is just shifting over the bit buff. We're going to discard that bit off of the bit buffer, right? Because we took a bit from the bit buffer and we put it onto the code, and now we're going to discard that bit. Now the count equals, we're going to dereference next and then increment it. Okay, yeah. And, okay, so we're doing some stuff with pointers, because next up here is, so how is it that we have what looks like not pointer logic and then some pointer logic? So next number of codes. So next is definitely a pointer. So what I don't get is, if next is a pointer, then what the hell is this? Yeah, I don't quite get that. If next is a pointer and we Is count a pointer as well? Okay, well, let's say count is a pointer, and okay, sure, it's a pointer, but then we add 1. Count is it's an array, right? So if we scroll up, count, yeah, count is it's an array of counts. So this right here is an array, and we're adding 1. So that is. So what I don't understand is. Okay, it's a pointer. We know it's a pointer, so shouldn't it be like, if it's a pointer, shouldn't it be like next equals h count, and then and we're adding 1. If we're adding 1, then instead of 0, it's 1 like that. What is the purpose of doing it this way? Well, first of all, this is dereferenced, right? And we're trying to get a pointer. Well, we are trying to get a pointer, so like we could do. Pretty sure we could do that, right? Obviously, that's more obtuse, I guess. So maybe that's why we're doing. But this should be equivalent to this. Okay, so that, yeah. Okay, so next is. Now, why is it. Okay, so this is purely for, on line 278, this is purely to prep everything to get it ready to work correctly in the loop. It's like seeding the loop, if that's even a word or a term. So somewhere else we have next, and yeah, so here we dereference next and then plus plus. Well, no, dereferencing next plus plus. That's going to increment the count. But where is next actually being changed, right? Because this is not changing next. Or, well, it depends on what binds tighter. Control F next, yeah. So seeing that that's the only place where next is being referenced, then it must be the binding order. It has to be doing this, and then it's dereferencing. So plus plus is binding tighter than this, because otherwise we wouldn't be able to get the next code ever. Because if we dereference and then increment, that makes sense, right? Because this the counts here are the frequency table shouldn't be edited, right? Because right now we are decoding, so it makes sense that the frequency table would not be altered. Now this is I feel like, this could be greatly helped by just some parentheses. So when we're looking at this, what that is this. That's right. So it's doing pointer arithmetic on next to get the next array entry, right? So changing the count index, and then it's going to dereference it to get the actual count value, right? But yeah, I feel like parentheses could be nice there. so dereference has less priority than plus plus. Let's make sure that's true. So operator, I'm going to look up operator precedence in C really quick. Operator precedence in C. Okay, C operator preference. Okay, so yeah, so suffix, postfix, increment, and decrement, it's like way up on the top here. So right here, plus plus is binding a lot tighter. And then indirection dereference is in the second category here. Sorry, so let me scroll here. So you can see that dereference right here is in the second category, and our plus plus minus minus, they're up in highest priority here. Therefore, plus plus, and then dereference. Therefore, yes, this is equivalent to this. So I guess if you know your operator preference, your operator precedence really well, then this doesn't matter. But holy crap, I wouldn't write it that way. I would, I don't know. I mean, in a perfect world where we all just know our operator preference, then I guess it's okay to write it that way. But why? I don't understand why you wouldn't. Like, it's only 2 extra strokes, and I think it makes it clear. Whatever. Okay. So we know what's going on here. So we get the count by incrementing now what I don't understand is because if we start at 1 here, oh god, it's even more complicated than I thought, because this is going to start at 1, right? Because it's count plus 1. So this is a post increment. So we're using the current value of next and dereferencing it, and then we increment. So even though this binds tighter, it's a postfix operator. So we use the current value of next when we dereference. So that's kind of a mind fuck right there, because even though this binds tighter than this, you could read it as this happens first and then this happens, which would be incorrect, but your calculations would come out the same. Yeah, I don't like this. Anyways, okay, 284, code equals code minus count less than first. So we've seen this before. Right, all of the codes are sequentially numbered. Therefore, the first code, the second code is going to be the first plus 1. The third code is going to be the first plus 2. The fourth code is going to be the first code plus 3. And therefore, let's say the code is the first code. So, if the code is the first code, well, then minusing anything except for 0 is going to get you less than first, right? And if the code is the second or the third code, and let's say there's 3 codes, then the third code minus 3 will get you before the first, because when you think about what the first code is, right? The first code the first code, let's say the first code is all zeros, and then there's one code minus, okay, yeah. Yeah, so I'm just working through this again. It makes sense to me. I described it in a previous video in a little bit more detail. But yeah, so I still get why that works. And so it's just to say that is the current code part of the current series of codes that starts at first and is this many sequences of codes, right? So you have so many canonical Huffman codes of a certain length and you have say you have 3 codes of length 7, and the first length 7 code is here, and then is this code within that set of codes is what it is. So it's just is the code within the set of codes denoted by first. So is this code within the set of codes denoted by the first Huffman code within that set of codes? Okay, so anyways, if the code is in the set of codes right here, then s member bitbuff equals bitbuff, s member bit count equals s member bit count minus len masked with 7. And 7 would be what does 7 look like in binary? 7 would be 3 bits, I think, 3 set bits. So in a calculator, really quick, let me get a calculator. Actually, we could probably use Google. 7 to binary. Yeah, 7 is 3 set bits. So that's also something I would be commenting, right? Like this right here. So it says heavily commented. It's more like heavily commented in the function description, so not really heavily inline commented. So 7 equals 0b, 111, right? Make a note of, what that mask is. And bit count minus length masked with 7. I have no clue what that means. And it is it's like, why are we editing the bit count right now? It almost is like, are we like, is this 7 kind of like erasing data? Yeah, I don't know. Just why 3 bits? Why are we... Yeah, I don't understand why we're masking... We're masking 3 bits. I don't get it. Okay, so bit count. Let's go look at what bit count is. Maybe I don't know what the hell I'm looking at. So that's in the state struct. So if we look at the state struct, bit count, discard leftover bits from current byte, assumes, nope, that's not the state struct yet. Okay, so state, so bit count, number of bits in bit buffer. Okay, bit count is the number of bits in the bit buffer. Okay, so So as we consume bits from the bit buffer, right, and put them into the code, right, so we're consuming the bits from the bit buffer, and then we're shifting the bit buffer over, then absolutely we want to change the bit count, right? If we're going to shift bits off, we definitely need to change the bit count. And so this is saying we're going to take off, we're going to but I don't know why it's an and, right? Because if we're going to take those 7 bits and reset all those bits to 0, how would that happen? Well, maybe that's what the len has to do with, right? If we yeah, because let's say if we have 7, right, and we subtract so let's take a look at this. So bit count, so if the bit count was 7, right? We have 7 minus 7, that equals 0, and then 0 and with the mask, right? 0 and the mask, right? That's going to lead to, 0, right? Because okay, that makes sense. That how you would and so you've effectively okay, but what I don't understand is why the mask. So bit count minus len, and then you're masking it with 7. But why? Why a mask at all? So so let's say the bit count is, I don't know, 14, right? 14, and you're gonna subtract, so len, I'm gonna guess, is, what can len be? There can be codes of different lengths, right? Len equals 1, and then somewhere we're incrementing len. Yeah, we're incrementing len. So 14, I don't know, let's say 14 minus 4 and 7. Like, what is there? Why is there a mask? I do not understand that. Calculator. So if I have something like 14, so 14 minus 4 and, okay, 14 minus 4 equals 10, and 10 to binary. Okay, 14 minus 10. Sure. And then if we mask it with 7, which is 3 bits, the 10 becomes 0b it becomes an 8. So is a mask of 7... Okay, yeah, so hold on. 1, 2, 3. 248, 504. Oh, are these all multiples of 8? 24, 16. So 8, if you add 8 plus 8 would be 16. 16, add another 8. 24. Uh-huh. 24. Plus another 8, 32. Yep. Okay. Plus another 8, 40. Plus another 8. Plus another 8, 48. Plus another 8, 56. Okay, yeah. So I'm looking at a calculator here. And, okay, so we know that there is a bit mask of 7, right? And, God, we need a better calculator. Yeah, this sucks. Okay, let's try to move. Okay, so top screen, maybe not. I thought this was my top screen. Why can I not? Is this not my top screen? Can I get any more annoyed here? Okay, this is definitely my top screen here, but it is not... Okay, so if we look at the calculator, and we have a bit mask of 3 bits, which is 7. And so we know no matter what the number is that these 3 are always going to be 0. So let's start counting out. We have 8, 16. Okay, add another 1, 24. Okay, the next number is going to be this set, and then we delete those, 32. Adding 8 again, 48, add 8 again, 56, yeah? Yeah. Right, so by putting that mask on, we are always getting a multiple of 8. And that definitely has to be important because, right, our buffer of binary, our buffer is in bytes. It's not in bits. So going back to here, we know that the buffer is working internally with bytes. So I feel like that mask definitely has something to do with that. So that's going to make sure that the... So I get that, but what I don't get is... Why is it... Okay, why is this mask working on bit count and not bit buff? Right? If the purpose is... Okay, well, 7 is only 3 bits. It's not 8 bits. It's 3 bits because then bit count is always a multiple of 8. Okay, that makes sense that why it's with bit count. So bit count is a multiple of 8, because 8 bits in a byte. Okay, so I get why I kind of get why the mask is there. I have a general idea of why the mask is there because the internal data is an array of bytes, not an array of bits. Um, and so what happens when... So when we take something and we mask off those bits, are we getting a lower number or a higher number? I think that's also important to think about. So let's go back to the top screen here for a second. Okay, so if we have some random ass number here, get these bits set, and 231, but we're going to mask off these bits here, right, to make sure we have a multiple of 8. 231, we're obviously going to get a lower number, right? Because we're going to get a lower number because we remove bits, so obviously. We're going to get a lower number, and that number is always going to be a multiple of 8. Okay, yeah. So let's look at the code again. So we know that bit count is going to be a lower number, and it's going to be a multiple of 8. So basically, we are subtracting this number of whatever from the bit count, and then we're rounding down to a multiple of 8. And that is, like, not obvious to me. But yeah, so we're going to subtract, and then we're going to round down to a multiple of 8. So right here. So right here, we're subtracting len, and then we're rounding down to a multiple of 8. And they're using the number 7 because you don't have binary literals in C, so there's no way for them to write that, and you can't really write that in hex. Well, yeah, you could write it in hex, but it'd just be 0x7, so it wouldn't really make a difference. Well, it would kind of. It would help me a little bit. But yeah, a binary literal would make a lot more sense right here. C does not have binary literals, which I think is a shame. And then... And so why are we rounding down to a multiple of 8? Well, when we fetch more bits... But we're only shifting the bit buffer over by 1 here. So why are we always... If we're only shifting over this bit buffer by 1 right here, I don't know why we are always going to mask to a multiple of 8. But anyways, okay, return next symbol. It's index code minus first. Right, so the codes, we're basically, what is this code's relative index related to first? Well, if the code is the first code, then it's first minus first. That gets us 0. And first is the code that is, like, if you put index in here, we get the first code, right? Or we don't get the first code, we get the first we get the symbol associated with the first code if we put index in here. Now if it's the second code, then code minus first equals 1. Code minus first equals 1, and that's index plus 1. So this lookup makes sense, because I've already went over it before. Still confused about why we're masking. I kind of have a vague hint, like I said, because I know that the internal buffer, the internal input buffer and output buffer, right? Those are both working with bytes. But yeah, okay. So while left minus minus, so index plus equals count, first plus equals count. Then we're gonna shift first over over one to the left, and then code we're also going to shift over one to the left, and then len plus plus. Yeah, I don't quite know. Let's see, left equals max bits plus 1 minus len. So the maximum number of bits in a code, I think. So we're on 295. Max bits is a define up here. So max bits 15. Maximum bits in a code. Okay. So left equals max bits plus 1 minus len. So let's say we have 15 plus 1 minus len. So it's basically 16 minus len. Max number of bits. If left equals 0, break. So I think there's a plus 1 because we don't have, there's no such thing as a code of length 0, I think. And that's why there's that offset of 1. The maximum, I don't know, maybe. The length of the code. So if the length of the code is 15, right? It's our largest code. Then 16 minus 15 is 1, right? And left would not equal 0, it would equal 1. And so we wouldn't break. Okay, so that kind of, okay, yeah, okay, that makes sense. And, okay, yeah, and then if we have 1, if left is only 1, then if left is 1, because we're on the highest, we're on the largest code, right? So the largest code is 15, right? So if len is 15, 16 minus 15, that's 1. Left equals 1. And that's important because when we go up to this loop, right, where we go left minus minus, we do not want to look at the smaller codes. We want to jump directly into those larger codes when we're looking them up in the symbol table. While left minus minus, code and because we're on the last code, we just have to we only do this loop once when we build up the code. Huh. What I'm kind of confused about is okay, we have this, but how do we ever really get back? I know it's an infinite loop, but the logic for re-entering this I don't quite make sense to me, but let's see what the logic here says. Okay, so the number of bits left. If left is 0, we break out of the infinite loop. If s in count equals s in len, then out of input, okay, so we've got it. So if we have, so what I don't get here is the equal sign kind of makes me uncomfortable. I feel like in count greater than or equal to s len, but I know like a lot of times when C programmers do their comparisons, they're like really exact about it. But okay, so if we have just read the last byte of input, denoted by in count, then in count equals in len, because the seek index, it's the last actually no, the seek index is equal to, well, it's not a seek index because in count is a count, it's not an index, so it's like the seek index, this is like the seek index minus 1, and if the seek index minus 1 is equal to the buffer's length, then we're on the last element within that buffer, and so we've read all the data, because we can't loop again, because we've already read all of the data, and therefore we're out of input, as this comment says. And then long jump is just C's way of doing a throw. So this is just like a throw statement is what this is, which is a way to like get out of this function, right? Because right now we're like are we doubly nested? No, we're just in one loop. Which I don't know why. Whatever, it's their way of destroying all of our stack frames and just jumping back to some arbitrary place in the code. Well, okay, so bitbuff equals x. Bitbuff equals our state, our input buffer, state dot incount plus plus. So we're going to use incount, right, which is our seek position. It's being used as a seek position, like I said, and then we're going to increment the value after we use it. That's what the plus plus is coming into there. So yeah, so that's the confusing, that in count it's being used as a counter, but it's also being used as a seek position. Okay, so then line 301, if left is greater than 8, then left equals 8. That has to do something with the fact that we're storing bytes, and there's 8 bits per byte. I'm not sure exactly what that has to do with it, but that's what it has to do with. Okay, anyways, after that, 303 is the end of our infinite loop. And then we have return 10 on 304, return -10, ran out of codes. And then 305, closing curly brace, 306, end if slow. And that's, yeah, that's the, what this right here is the fast function. It's just the end if or if slow or if not slow. So yeah, I still don't quite understand the mask here. But it but I understand why I kind of get that. Yeah, it has something to do with the fact that our input and output buffers are storing bytes, and by masking with a 7, we are rounding or rounding down to the nearest multiple of 8. So I guess now what we have to do is, now that we know that when we're thinking about the number of bits that are used up, we always round. So we're going to subtract the number of bits that are used up, but then we're going to round that number down to the nearest multiple of 8. And then bit count. Where else is bit count referenced? Left equals bit count, but okay, nowhere, huh? Yeah, that's the only place it's being. I mean, it's in left. It's in left, but that's outside of the loop. After that, it's only being changed here. And left. So len is, how is len getting set? Is len somehow related to left? Len equals 1. Len plus 1. Oh yeah, len is somehow related to left because left plus plus here, and then len plus plus down here, so they're kind of bound together. And then left is based on the bit count. So when we're looking at left is going to start out as the bit count, and as left goes down, as left is going down, len is going up, right? As left is going down, len is going up, and they're both related to each other. So len is eventually going to be equal to bit count, and when len once len is equal to bit count, then this will get to, if len is equal to bit count, then we just get 0 from this, right? 0, and then we mask with 7, right? We round down to the nearest multiple of 8, but it's already 0, so that has no effect anymore. Okay. Yeah, I still don't quite get it. I think I'm just gonna keep on reading through more of this code, because this is the fast version of decode, and I already understand the slow version of decode, so I don't really need to understand the fast version, because I just want to write something that works. I'll worry about optimizing later after I can wrap my head around just making something that works, you know? So I'm not quite sure why that's there. Maybe I'll be enlightened later and have a eureka moment after I understand this a little bit more. But I think for now, I'm gonna give the fast version of decode a rest, and I'm just gonna keep on reading more of this source code. Okay, we have a block comment on top of the construct function. The comment spans lines 308 to 339. So if I scroll down here so you can see it, there's 339 way down there, and there's the construct function. We're going to read this comment first, and then we will read the body of the code. Given the list of code lengths, length 0, n minus 1, so that's 0 to n minus 1 inclusive, representing a canonical Huffman code for n symbols, construct the tables required to decode those codes. Those tables are the number of codes of each length, and the symbols sorted by length, retaining their original order within each length. The return value is 0 for a complete code set, negative for an oversubscribed code set, and positive for an incomplete code set. The tables can be used if the return value is 0 or positive, but they cannot be used if the return value is negative. If the return value is 0, it is not possible for decode using that table to return an error, any stream of enough bits will resolve to a symbol. If the return value is positive, then it is possible for decode using that table to return an error for received codes past the end of the incomplete lengths. Not used by decode, but used for error checking. H member count 0 is the number of the n symbols not in the code. So n minus h member count 0 is the number of codes. This is useful for checking for incomplete codes that have more than one symbol, which is an error in a dynamic block. Assumption. For all I in 0, n minus 1, 0 less than or equal to length I, less than or equal to max bits. This is assured by the construction of the length arrays in dynamic and fixed, and is not verified by construct. Format notes. Permitted and expected examples of incomplete codes are one of the fixed codes and any code within a single symbol, which in deflate is coded as 1 bit instead of 0 bits. See the format notes for fixed and dynamic. Within a given code length, the symbols are kept in ascending order for the code bits definition. Okay, so now we're on to the body. We have local int construct with parameters h, length, and n. H is of type Huffman. Length is of type short, and it's constant, so it's immutable. And int is, and n is of type int. So let me read that whole definition without being weird and just say it verbatim. So on line 340 we have local int construct open paren struct Huffman pointer h, const short pointer length, int n close paren. Line 341 we open up the function using a curly brace. Lines 342 to 345, we have some variable declarations. We have symbol, len, left, and offs. Offs is an array. Symbol, len, and left are ints. And offs is a short. It's a short array, sorry. It's an array of shorts. Let me read the definitions as they are written. So line 342, int symbol, current symbol when stepping through a length. 343, int len, current length when stepping through h member count array. 344, int left, number of possible codes left of current length. Line 345, short offs, open square bracket, max bits, +1, close square bracket, semicolon. Offsets in symbol table for each length. Okay, so let's scroll down to the first piece of logic, 347 to 353. On line 347, we have a comment describing this block of code. Count number of codes of each length. For len 0, len less than or equal to max bits, len plus plus, h member count len equals 0. So I think this is just zeroing out everything before it starts the counts, right? So I'm guessing the yeah, because we did not we declared these. I'm not sure. I guess it's because if you run this multiple times, your array needs to be reused, so it wouldn't be 0 initialized after the second run, and that's why we are clearing all of the members using 348 to 349. Okay, so then 350 to 351 for symbol equals 0, symbol less than n, symbol plus plus. Okay, and h member count, and then within count we have length symbol. So we're looking up the length of a symbol and then figuring out and then incrementing the count. Okay, so the count is so we're building the frequency table here. The frequency of symbols of certain lengths. So the count, right, is just a histogram of how many symbols of this length do we have, how many symbols of that length do we have. And for each symbol, right, we have to put it somewhere in the histogram, and that's what's happening here on line 351. Assumes lengths are within bounds. Okay. So basically, if we've only allocated so much space in this count array, and if the length is out of bounds, that would be a problem. That would be a seg fault. Line 352, if h member count 0 is equal to n, we have no codes. Let's see, why is that again? H member count 0. Oh yeah, because 0 is you can't have a code of length 0, and it's set up in the comment on the top of the function that 0 is going to be a check for the number of codes that are not present. If the number of codes not present is equal to all of the symbols that we're going through, right? Because on line 350 we see symbol less than n. So if the number of codes that are not there is equal to the number of symbols we're going through, then it means we don't have any codes. Line 353, we're going to return 0 if we have no codes. Complete but decode will fail. That's what it's saying. Okay. On line 355, we have a block comment for the code spanning lines 356 and 362. Line 355, check for an oversubscribed or incomplete set of lengths. On line 356, we have left equals 1. One possible code of 0 length. 357 to 362, let's read this code. For len equals 1, len less than or equal to max bits, len plus plus. Left, bit shifted over by 1. 1 more bit, double codes left. Line 359, left minus equal, h member count len, deduct count from possible values. Line 360, if left is less than 0, return left. Oversubscribed, return negative. Left greater than 0 means incomplete. And then on line 362, we're just closing off the for loop. Okay, so let's actually try to figure out exactly what this means. So we're checking for an oversubscribed or incomplete set of lengths. And max bits. What was max bits? So I'm gonna open up another copy of this really quick. I'm gonna take a look at what max bits was, because that is declared up here at the top. So max bits 15, maximum bits in a code. So basically, the length of the actual binary string can't be more than 15 bits. Okay. And with knowing that, max bits here, if we had something, we can't be looking at anything greater than max bits because we only allocated enough memory in our arrays for, and well, hold on, that's not even what we're supposed to look at. We're looking at this. But same deal, we only allocated enough memory in all of those arrays to store indices 0 to 15 inclusive, so 16 slots. So that's why we're doing less than or equal to max bits. And left, check for an oversubscribed or incomplete code set. So left, okay, so we're starting with a code of 1 bit, I think. Right, this is a 1-bit code, right, which you start out with length 1 and the actual binary. So this is like a binary mask here, I believe. And the first time through, that binary mask is, well, if we start at 1, then this is going to be too long after we shift it over. Let's see. So we shift it over, and then we go left minus equals h count len. So I think this requires me to have more intuitive understanding of the Huffman codes, because it looks like we're doing more math on Huffman codes is what's going on here on line 359. You know what, now I still think this is 1 filling, because for this to happen, we would want the maximum value, and then we're going to like just remember that Huffman codes are canonical, so even though you want to think of a Huffman code as binary, you can still count with them, right, by adding and subtracting to go from the first to the next or whatever. So if we shift here, and if this is 1 filling, then we start off with the maximum possible Huffman code, and then by decrementing, we're kind of like going through each code of the current length, and we're just decrementing 1 because we're taking the total number of codes of this length, and then we're just decrementing, and that would have some type of significance, because I think if we're what would happen if how would we know if we were going to collide with something else? If left is less than 0, well, that would definitely indicate, if left is less than 0, then that definitely indicates that we're colliding with something. Oh, you know what? This shift here is not 0 filling. That's why we can always do if left is less than or equal to 0 when we are decrementing that Huffman code. Oh, and that's also why this is shifted over more than I would think, right? So we start off with 1 for the binary, and the length is 1, but then we shifted it over, so the binary is 1, 0. Right? Because for the Huffman codes of length 1, we can have 2 of them, right? We can have either a 0 or a 1. So if we have a 1, 0, and we subtract, so we're dealing with binary here. If we have a 1, 0, and we subtract a 1, then we're going to get just a 1. And then if we subtract 1 again, we're going to get a 0. So we subtracted twice, and we're at 0. So we have 2 codes, which is correct. But if we subtract 1 any more than that, we subtract 1 more time, then we're going to end up with a negative number, and then left is going to be equal to 0. And therefore, we have our oversubscribed code set. Okay, yeah. So this is not one filling. I need to actually run some code with this because I've never used this operator. I mean, we can just look at it. Because I was pretty sure it's like a, it's like a, yeah, it's like one of, right? It's like one of these or these. But instead it's using shift, so it's the same type of thing. So assignment by bitwise shift, assignment by bitwise left shift and right shift. Yeah. Okay. So I am understanding that code correctly. So lines 355 to 362 we are done with. Check for an oversubscribed or incomplete set of code lengths. Okay, so let's scroll down to the next block of code. Generate offsets into symbol table for each length for sorting. That's line 364. And on lines 365 to 367, we have the code for that. So we have offs 1 equals 0 for len equals 1, len less than max bits, len plus plus. Offs len plus 1 equals offs len plus h member count len. Okay, let's actually think about what that means now. Generate offsets into symbol table for each length for sorting. So first thought is, what is our symbol table? Well, there's only one thing it could be because there's only one assignment here, and that is on line 367. We are accessing the offs array. So I'm going to look at this extra copy I have of this code because I'm a little bit we're on line 378. So 378, or not 378, hold on, 375 more like it. Okay. So offs is where are you declared? So we have it right up here that offs is offsets in symbol table for each length. I don't know what that means. Offsets in symbol table for each length. So we're talking about, we have a whole bunch of symbols, and the symbols have different lengths, yes. But what do they mean by offset? Do they just, is offset just another word for lengths? But then that would just be, yeah, I don't quite understand what offsets is. Offsets in symbol table for each length. And max bits, right? So this is the binary length of different things. And if our code was, if the maximum code length could only be 1 bit, then we'd still have to add 1 because we would want the slots 0 and 1 within this offs. So that makes, so this allocation size here, that makes sense to me. But as far as what is offs, I'm not sure. Or I don't have a clue. So generate offsets into table for each length for sorting. Okay, so offs1 equals 0. And this is the same code I'm looking at over here now. Yeah. Offs len plus 1. I'm thinking that maybe it's maybe offsets for jumping over symbols that don't exist. That's the thought. Maybe it's when you create Huffman codes, when there's symbols that don't exist or there's a high frequency of a certain type of symbols, the binary can skip over like imagine if we have a whole bunch of well, no, if I don't know. I'm just imagining we have a set of codes that use 4, and then we have a set of codes that's like this, but we don't have anything in between. So you would need some type of offset to describe that there's this offset between here and here, but I'm not sure that's a correct assumption either. Generate offsets into symbol table for each length for sorting. Okay, well, what is it actually doing? So on line 367, oh, and it's referencing itself, because offs1 equals 0. So I'm guessing for the code of length 1, there's a 0 offset. So I think I'm onto something with kind of thinking of this. I'm not sure. Okay. So let's take this. And we know that this is kind of what we're thinking about. And so let's say the count let's say count 1 is like A, B, right? And so there's like 2. Not sure how we should. So let's say count A. Oh. And C, D, and E. So let's say 2 has 3. And let's do like 5. Okay, and then so if we're looking at something like this, now C, D, E, F, G, H. So the codes don't necessarily encode ASCII letters because they are encoding bytes, and there's 8 bits in a byte, and ASCII is only 7 bits. What I'm using letters just for convenience here. Okay, so this is our count in len, and we have lengths 1, 2, and 3. And if we look at the code here, len is starting at 1. So really, we should just take all of this. Take all of this, paste that there for reference. We can get rid of this for now. And we can get rid of this extra line up here. So the offsets, len starts at 1, right? So that means offs 1 equals okay, wait, hold on. So len plus 1, 2, right? And that equals offs 1 plus the count for that len, right? And for this right here, that would mean that offs 2 equals offs 1 is 0, right? Yeah, offs 1 is 0. And then the count for this current length, or length 1, is 2. So offsets 2 is telling us how do we jump to the C, right? And offs 1 is 0. So we're like 0. So if we're looking at the offsets, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So so really what we're looking at here is offs 1 is here, offs 2 is here, and then like offs 3 is here, right? Because we're taking the is that correct though? Hold on. Offs. Len starts at 1, but this is, oh, my bad. This is 0. Len starts at 0, so it's like this. This entry, right, is offs len. So that's equal to 0. So yeah, 0. Yeah, so oh, no. I'm still wrong again. Because offs 1, we do not change, because this is 2. This is offs 2. So offs 1 is seated at 0. Offs 1 is always 0. So the first thing we assign is offs 2. Offs 2 is here. And to get that, we look at the previous offset. So we start from the previous offset. So starting from the previous offset and adding the count for that length. And the count for this length right here is 2, right? So that definitely gets us here. And then the next time through, we start off from where we are and add the count again for that current length. So the count for length 2 is 1, 2, 3. And 2, so 2 plus 3. So 2 plus 1, 2, 3 puts us here at this offset. And so it is definitely some type of like way to jump or skip over clusters of symbols. I don't know exactly what the reason for that is, but I kind of can see how something like that could be useful. So we'll just put this in our like little notes where we've been kind of doodling to try to like understand how things are working here. So we'll take this and we will we already have the code, so this is in construct function. So we can just make a note that this is notes on some code in construct function. So offs is just like this way to know and it's how to get to the first it is how to get to the first yes, it's how to get to the first symbol.
Are you still no caffeine?
Yeah.
Okay, never mind. I won't offer to
Okay.
make you some coffee.
So it looks like it's how to get to the first symbol. It's how to jump directly to the first symbol of a certain length is what offs is. So where offs 1, we have symbols of for symbols of length 1, how do we jump to the first symbol of length 1 in some type of continuous array of all of the symbols? Right, so we have all these symbols and we are lexigraphically sorting them, right, because that's kind of like part of how Huffman codes work. We're going to lexigraphically sort all of the symbol and assign them Huffman codes. So how do we jump within that lexigraphically sorted list? How do we jump to the first symbol of that length? And we'll use offs 1, which is 0, and we'll put us right here. Well, how do we jump to the symbols of, length 2? Well, we're going to do that by just looking up that offset, and we see the offset for that is going to be 2, right? So offs 2 equals 2, and that puts us at the first symbol of that length. So really, it might make more sense if well, this is saying that, these symbols are getting like, this is totally invalid because if we use 0 and 1 for Huffman code, then we can't use anything else. But just for the sake of visualizing this, right? Right, so maybe A equals this, and B equals that, and then C, D, E equals, right, and then F, G, H, right, these are our length 3 symbols, so those equal 1, 2, 3, like that. But yeah, it's just a way to be able to, within our lexigraphically sorted symbols, how do we jump to the first symbol of a given assigned length? Okay, so I kind of get that now, and with that, um, so this I would just call it's I guess it's not a jump table because a jump table I believe implies inputting index and then getting a function out. But similar concept, except we're just it's almost like a I would almost call it like a offs here is kind of like a seek table, is what I would call it, you know. So I would call offs a seek table. I just made that up. I don't know if there's an actual term for that. We could actually look that up really quick. Seek table. Yeah, I don't know. I think it's valid. I'm going to use that term in my code to understand what the hell I'm talking about, but I don't think it's necessarily an actual computer science term. Okay, so let's look at the next block code here within the construct function. Yeah, we're still in the construct function. On lines 369 to 370, we have a block comment. Let's read that. So did I say 370? Jesus. 369 to 372. Put symbols in table sorted by length. The symbol order within each length. Oh, put symbols in table sorted by length by symbol order within each length. On lines 373 to 375, we have some code here. Lines 373, for symbol equals 0, symbol less than n, symbol plus plus. 374, if length symbol not equal to 0, then h member symbol, and this is kind of a complicated lookup here. We're going to take a symbol, we're going to look it up. Within symbol, look up using offs. Offs, look up using length. Length, look up using symbol. And then once we look up that symbol using the offs, we're going to increment offs. Interesting. Is that to account for... Why are we incrementing offs? One thought is the algorithm given above doesn't account for symbols that just don't occur at all. And so if the jump is 0 in that seek table of offs, the seek table here, if the jump is 0 in one of them. So here, imagine that one of these clusters, instead of having 3 members, imagine that this only has 0. That would mean that when calculating if this was 0, offs 1 would still be in the same place. Offs 2 would still be here, which wouldn't make any sense because it's 0, so it's just on a spot that doesn't touch these, but it doesn't make any sense. And since it's 0, because this is 0, that means offs 3 would be in the same exact spot because we add 0. And so offs2 and off3 would be at the same spot. So imagine that there's no slots here, right? So if we did something like, so we just made this into equals 0. Right, so then this would be 0, 1, and since there's 0 of them, actually this would be 1. Right? Because it's the count of the previous one, or no, the count of the previous one would be 1, 2, so that would be like that. And then the count of the previous one here would be 0. And so you'd start here like 2, 3, 4, 5, 6. But yeah, so this I think would be a problem if both of these are starting at the same. Hold on. If both of these are starting at the same index, like here, because this says if count 2 has nothing, then we're over here for this one. For offs2 is at 2, but then offs3 is also at 2. So just I'm not sure if that is what that is about, though, with this plus plus here. That's just my guess, because if we always if we always do a plus plus to these offs here, then we would never have, they would never be identical like this, right? And maybe we don't want to start at 0, so if we did plus plus to this, we'd have a 1. We'd have 1 and 2, right? And then this would intersect with the previous, but then we do a plus plus, that'll give us a 3. And then this right here, which is still a 2, well, now we plus plus, and then that's 3 and 3, so now that doesn't make sense. So let's take this for a second. Let's take that, and let's look at this. So the first thought is, the first thought is doing something kind of like this, where we can kind of I don't know if this will help or not. And the plus plus, so here's this. So we're going to look up the offset. So we're going to get the current symbol. So whatever we're doing, we're going to look this up. And that's going to give us a certain symbol. But then we're going to increment the value within. We're going to increment the jump. It's going to change what symbol you get, though. Put symbols in tables sorted by length, by symbol order within each length. So we take the symbols, we get the length, and that gives us the offset. Oh, okay. So, right, this offset starts at the first. Starts as the first, right? So the offset for a symbol of length 3 starts here, right? And then if we do that plus plus, the next one's going to be here, the next one's going to be here, plus plus, plus plus, right? So this plus plus is so we don't use up the previous offset slot. So mark previous offset okay, so I get what that's doing there. Okay, so I get how we're marking the offsets like that. Now, yeah, so this symbol, and then we're going to look it up. So this offsets table, right, jumps into the symbol table at the correct offset to get out the symbol that it wants. And then we have a... Oh, and this symbol here, right here, isn't assigned to anything yet. So this is where this assignment right here is happening. Right? So equals symbol. Okay, so, okay, now I get kind of what's going on there. Okay, yeah, so that makes sense now. So let's keep on going on here. I'm afraid that, like, after all of this time that I'm spending here, that I'm gonna read through it another time, and I'm gonna be like, I'm not gonna know what it meant again, and that's gonna be kind of annoying. But I think that as long as I know what the different functions are doing, then I can kind of slowly transcribe my own version. And when I transcribe my own version, I'm going to create better names, and I'm also going to like put more of these kind of like diagrams into my code so it can be understood. They say that this code is heavily commented, and yeah, I get that. I get that the I guess it is pretty heavily commented. It's just that working through some of the logic here takes a little bit for me. Okay, so we know how that is going to do the it's going to create our table of symbols, where the symbols are all ordered by length. Okay, so let's see what's next. 377. Return 0 for complete set, positive for incomplete set. And do we still have our timer going? Yeah, we do. Okay, and then left. So we just return left. Where is left in here? And that's not what I wanted. I don't know why the fuck it just... Yeah, so it just decided to kind of like jump to wherever it felt like when I did that, and that's kind of annoying. Okay, so return 0 for complete set, positive for incomplete set. And so we know what we really want is a 0, but where is... Okay, so if it's negative, we're already going to return it here. Positive for incomplete set. Okay, so up here is where left is going to end up positive if, no, okay, left is... Yeah, this is where left would end up positive. And if it ends up negative, we immediately exit. But if it ends up positive, then we just keep on going anyways. Okay, yeah. So that makes sense. So that is the end of the construct function, and I think I got a good handle on what the construct function does. So I'm going to stop recording this here since I'm going to do one recording per function basically as I kind of read through it. Looking at the codes function now, there's a big block comment on lines 381 all the way down to 435. So I'm going to read that block comment first at the top of the function, and then we'll read the body of the function. Decode literal/length and distance codes until an end of block code. Format notes. Compressed data is after the block type if fixed or after the code description if dynamic, is a combination of literals and length/distance pairs terminated by and end of block code. Literals are simply Huffman-coded bytes. A length/distance pair is a coded length followed by a coded distance to represent a string that occurs earlier in the uncompressed data that occurs again at the current location. Literals, lengths, and the end of block code are combined into a single code of up to 286 symbols. There are 256 literals, 0.255, 29 length symbols, 257, 285, and the end of block symbol 256. There are 256 possible lengths, 3.258, and so 29 symbols are not enough to represent all of those. Lengths 3.10 and 258 are in fact represented by just a length symbol. Lengths 11.257 are represented as a symbol and some number of extra bits that are added as an integer to the base length of the length symbol. The number of extra bits is determined by the base length symbol. These are in the static arrays below. Lens array for the base lengths and lext for the corresponding number of extra bits. The reason that 258 gets its own symbol is that the longest length is used often in highly redundant files. Note that 258 can also be coded as the base value 227 plus the maximum extra value of 31. While a good deflate should never do this, it is not an error and should be decoded properly. If a length is decoded, including its extra bits, if any, then it is followed by a distance code. There are up to 30 distance symbols. Again, there are many more possible distance, 1.32,768, so extra bits are added to a base value represented by the symbol. The distances 1.4 get their own symbol, but the rest require extra bits. The base distances and corresponding number of extra bits are below in the static arrays dist array and dext array, dext. Literal bytes are simply written to the output. A length/distance pair is an instruction to copy previously uncompressed bytes to the output. The copy is from distance bytes back to the output streams. The copy is from distance bytes back to the output stream, copying for length bytes. Distances pointing before the beginning of the output data are not permitted. Overlapped copies, where the length is greater than the distance, are allowed and common. For example, a distance of 1 and a length of 258 simply copies the last byte 258 times. A distance of 4 and a length of 12 copies the last 4 bytes 3 times. A simple forward copy ignoring whether the length is greater than the distance or not implements this correctly. You should not use memcpy, memcopy, since its behavior is not defined for overlapped arrays. You should not use memmove or bcopy, since though their behavior is defined for overlapping arrays, it is defined to do the wrong thing in this case. Okay. So that's the entire block comment on the function codes. Let's look at the actual function. So on line 456, we have local int codes, open paren struct state pointer s, comma, line 437, const struct Huffman pointer len code, comma, line 438, const struct Huffman pointer dist code, closing paren, and then on line 439 we open up the function with a curly brace. So going over that signature one more time, the function returns an int, and the function name is codes. It takes 3 parameters, and the parameters are s, len code, and dist code. S is a pointer to the state struct. Len code is a pointer to a Huffman struct, and dist code as well is a pointer to a Huffman struct. So both len code and dist code are pointing to Huffman structs. So, oh boy. Okay, well, let's just deal with it. Okay, so on lines 440 to 442, or wait, actually we have many more declarations than that, because we also have these hard-coded arrays. Okay, so it's lines 440 to 456. We have some variable declarations. We have int symbol, which is the decoded symbol. We have int len, length for copy. We have unsigned dist, distance for copy. 443, we have static const short lens, 29 members, equals, and then we have a whole bunch of numbers which I'm not sure how they derived these. I was looking at somebody else do a PNG decoder, and they said that this was just the result of tweaking algorithms and coming up with what the best values were. So let's see. 446, const short lext has 29 members. 449, const short dists has 30 members. 453, static const short dext has 30 members. So let's go over what all of these arrays are. So we have 4 arrays, and they're all static const short. We have the arrays lens, lext, dists, and dext. And right off the bat, I noticed that lens and lext are both 29 in length, and dists and dext are both 30 in length. So I believe they're paired arrays, where lens, right, because lens is the lengths, and then lext is the extra bit for those lengths. Dists is distances, and dext is the extra bits for the distance codes. So those are both paired together. Lens is paired with lext, dists is paired with dext. So let's look at the comments describing what these are. So static const short lens, open brace 29, close brace, is size base for length codes 257 ... 285, sorry, 257 to 285. Lext is 29 elements, extra bits for length codes 257 ... 285. Dists with 30 elements, offset base for distance codes 0 ... 29. Dext 30 members, extra bits for distance codes 0 ... 29. Okay, so the actual numbers, I don't know if it's significant because they seem kind of, they're probably not arbitrary, but they're like probably the result of what do you call it? They're probably empirically derived numbers, right? They're probably derived from testing the algorithm over and over again. But let's go over it. So lens here, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 11, nope, there's no 12, 13, 15, 17, 19, 23, 27, 31, 35, 43, 51, 59, 67, 83, 99, 115, 131, 163, 195, 227, 258. for lext, we have 0, 0, 0, 0, 0, 0, 0, 0. So that is 8 zeros. Yeah, 3 and 3 is 6 plus 2 more. That's 8 zeros in a row. Then 1, 1, 1, and another 1. So 4 ones in a row. 2, 2, 2. So 4 twos in a row. 3, 3, 3, 3. So we have 4 threes in a row. 4, 4, 4, 4. So we have 4 fours in a row. And then 5, 5, 5, 5. So we have we have 4 fives in a row, and then we have another 0. So 8 zeros, 4 ones, 4 twos, 4 threes, 4 fours, 4 fives, and then a 0. And that's in the lext array. Dists, we have 1, 2, 3, 4, 5, then 7, 9, 13, 17, 25, 33, 49, 65, 97, 129, 193, 257, 385, 513, 769, 1025, 1537, 2049, 3073, 4097, 6145, 8193, 12289, 16385, and 24577. Okay. For the last array, we have dext. Dext has 4 zeros in a row. Then we have 2 ones, 2 twos, 2 threes, 2 fours, 2 fives, 2 sixes, 2 sevens, 2 eights, 2 nines, 2 tens, 2 elevens, 2 12s, and 2 13s. Okay. So let's try to take a look at the actual code. I believe this is going to be a little bit more difficult. So we might want to read through it all first and then try to figure out what's going on. So decode literals and length distance pairs. So we have a do loop, and this do loop goes all the way down to, it's a do while, it looks like, because we have a while down here. While symbol not equal to 256, and then after that loop it says done with valid fixed or dynamic block, return 0, and that's the end of the function there. So let's try to make sense of this do loop. Decode literals and length distance pairs. Symbol equals decode, and then it has the state struct, and then it has len code. Okay. So len code is a Huffman struct, and we're just going to pass it to the decode function, which we've already went over. So let's not worry about how that works. We just know that it's going to get us a symbol. Okay. If the symbol is less than 0, return the symbol, and it says invalid symbol. If the symbol is less than 256, then it is a literal symbol. Okay, so the comment says literal symbol is the byte, right? So literal symbols are always byte values. That's why less than 256. So we cover 0 to 0xFF, right? But they're denoting it with, I'm not sure why they don't use hex in this case. I feel like hex would be more readable, but whatever. 464, write out the literal. So if it's less than 256, if s member out not equal to nil, so if the output buffer exists, basically, then if s member out count equals s member out len, return 1, and I believe that's because you're out of the output buffer has no more memory, from what I was reading before. because the seek position out count is already resting at the end of the array. Okay, so for 68, s member out, and within that we're going to use array access with s member out count equals symbol. And then outside of this if out not equal to nil, we do s member out count plus plus. So that's interesting that here, because everywhere else they've been doing the post incrementer within the array accessor, or within the array accessor. So I'm not sure why they don't do it here. Oh, they don't do it there because we want to increment the out count no matter what, even if there's no output buffer to write to. We always want to increment out count, and that's why they're doing it where they are on 470. Okay, so that makes sense. So we have symbol less than 0 for invalid symbol. This is a literal symbol, and then else if the symbol is greater than 256. So what is, 256 must be end of block code, right? I believe. Because you notice here, less than 256 and greater than 256. So we're skipping over 256 here, but I believe 256 is the end of block code from what I was reading earlier, if I remember correctly. So if the symbol is greater than 256, it is a length. So it's not a literal symbol, but it's a length. Get and compute length. Okay, so we have symbol minus equals 257. So we're minusing 257 because the first length code is starting at 257, right? Because greater than 256. So I feel like greater than or equal to 257 might be more readable, but whatever. But we're going to remove that offset so that the first symbol at 257 starts at 0. Does that make sense? Okay, yeah, that makes sense. So there can be a length of 0. Does that make sense? Why would you do that? Oh, well, that's what it's saying. Symbol minus equal 257. Okay, yeah. So if the symbol is greater than or equal to 29, return -10, invalid fixed code. And that makes sense because if we look at our arrays here, right, we have 29 here, right? So any more than that, and we can't actually access any member in the array. Okay. So invalid fixed code, return -10. Lens equals lens symbol plus bits. So we're going to get some bits, and we're going to get the extra bits. So this is length extra. So the length extra bits for a given symbol. Okay, and the symbol in this case is just an index, right? So it's just an index accessor. And lens symbol. Okay, and so we combine both these arrays, the base length plus the extra amount of bits for that symbol, and that gives us the final length value. Okay, that makes sense. I don't know exactly why they do it this way. This seems very convoluted and complex, probably something I'm not remembering, but I know what they're doing. I don't exactly know why the algorithm is that way, but that reasoning can't really be derived just from looking at the code. So I understand as much as I can from looking at that at line 477. Okay, so 479, get and check distance. So it should be kind of like the same thing, very similar thing. decode S dist code, right, which is pretty much the similar to the symbol equals decode S len code. So I imagine the logic is going to be very similar, but we're going to be looking at the dist codes instead of the len codes. So let's go back up here. Get and check distance. That's on line 479, that comment. 480, symbol equals decode S. So that's our state struct and our dist code Huffman object. 481, if symbol is less than 0, return symbol, invalid symbol. And if it's less than 0, negatives already indicate an error, and that's why we can just return the symbol itself. 483, dist equals dist's symbol plus bits s dext symbol. Okay, so same thing as earlier. We get the base distance for that symbol, and then we get the extra bits for that symbol, and that gives us the final distance code. And now we have a length code and a distance code. So inflate allow distance too far. So I looked this up. This is a common thing that decoders do wrong. So many people got this wrong that they had to make a define for it so that if everybody does it the broken way, then even though the right way is technically right, it's incompatible with the way people are doing it, if that makes sense. But yeah, so like I believe I was looking at this and I was thinking this might be why Macromedia Flash or Adobe Flash did weird things with PNG files where I could never get max intensity red, green, or blue channels. It would go up to like 250, 254, but never 255. And I believe, this might have something to do with it. It's just a hunch. But anyways, inflate allow distance too far array. I could be totally full of shit, but anyways, let's look at it. If dist greater than s member out count, return -11, distance too far back. Oh, hold on. That's a not def. Sorry, this is a not defined. So this is the proper behavior right here, right? If the distance is greater than out count, return -11. What does that actually mean, though? So if we look at out count in the state struct, state out count, bytes written to out so far. Okay. So that kind of makes sense because we would be jumping over. I'm pretty sure if we allow distance too far, we're going to jump over sectors of memory in the output buffer that have not been touched. And you could get garbled data if that memory was not cal-locked, like zero initialized before we started writing to it. That is my guess of what would go wrong if we allowed this scenario, but I'm not quite certain about that. And return -11. Okay, anyways, and if and so this is going to happen no matter what. Copy length. Sorry, hold on. Yeah, so right. Okay, yeah, so right here, is this on screen? Yeah, this is on screen. Right here, that's going to happen no matter what. Copy length bytes from distance bytes back. Okay. So Is this where we finally use the length and distances? Yeah, we got len and we have dist here in the code. So yeah, if s member out not equal to nil. So if we have an output buffer, then we're actually going to deflate the data. Otherwise, we're just hackishly trying to figure out how much memory needs to be allocated by doing like a dry run of the deflate without actually writing to memory. If s member out count plus len is greater than s member out len, return 1. And that is why. Yeah, that's out of, this is a buffer overflow right here. So we're just checking to make sure that we're not overflowing our output buffer. Yeah, because out count is the size of the output memory. So out count bytes written to out so far, and then out len is available space at out, right? So if, well, that's nice. Okay, there we go. I don't know what that was about. So yeah, out count plus len greater than out len, then yeah, we can't, we're about to write outside of our output buffer, so we return 1. Okay, and this is a problem. This is an error. While len minus minus s member out count equals okay, so we're gonna decrement len here, but then out count we're gonna be incrementing. So we're going to write len number of bytes to the output buffer by kind of indirectly using out count. I kind of get why they do that. I think they're kind of being efficient with memory here. Maybe. I think it would be much better just to have a for loop that loops over len, and then we just set out count correctly, rather than doing this, I don't know, this weirdness here. But whatever, this is how they do it. So if we allow people to do stupid stuff, then on line 496 and 497, we have kind of like a, or kind of like injecting a what do you call it? It's not a trinary statement. What the hell is it called? Ternary. It's a ternary statement is what it's called. Yeah, it's a ternary statement. So we're injecting a ternary statement right here. And this is dist greater than s member out count question mark. And if we're outside of, if we've gone too far, we're just gonna write a 0. Yeah. Otherwise, we're just gonna do the normal behavior. And in the case of not allowing this behavior, then we don't even have to check for this condition because it just because we already did not allow it. The reason why it's broken over 2 sections here, I believe, is because this is C code, and just throwing anywhere you want probably is not acceptable way to do this. So there's this macro is being used in 2 places for the sake of being able to gracefully fail is the reason why I think it's like this. But anyway, so we can kind of ignore this, right? We can just ignore this because we want to think about the proper behavior. But understanding how it works when it doesn't have the proper behavior, I guess that was good to kind of get a feel for. But we'll ignore this highlighted section and just look at s member out count. So we're just going to write the byte to this position, and it is equal to s member out count minus dist. So it's the distance backwards, I believe. And then out count plus plus. Okay, so the way it's going to take the so it's going to start from the distance backwards, and then it's going to copy forwards, and it's always the, yeah, that makes sense. So it's so it's the first byte of this distance backwards, and then to get to copy the next byte of that distance backwards. Well, the next time we go through this loop, out count is incremented by 1, meaning that this will go 1 byte less backwards to get the next byte we're looking for, and that will effectively copy a chunk of memory a certain distance backwards to the current position. Okay, so that makes sense to me. We could kind of like go over how that works maybe really quick, since I have been kind of like making notes. So let's say so let's say we are here at x, and we want to from here we want to copy all of this, right? And this is 1, 2, this is 1, well, first of all, this is 1, 2, 3, 4, 5, it's 5 bytes. Actually, let's not do 5. Let's put a 4 here because I don't like it when the numbers are the same. 1, 2, 3, 4, 5, 6. Okay, so that's 6. So this is 6. Oh, sorry, you can't see that. So this is 6. We're starting at x, and we want to copy all of these bytes. So we want to go back a certain amount. So we want to go back 6, right? 1, 2, 3, 4, 5, 6. We want to go backwards 6, and 6 is also the length of the section we want to copy. So the distance backwards is also the length of well, it's not. It's technically not, because we could go let's change this up. Let's say we only want to take 4. No. Okay, now I gotta put a 3 here. So let's say we want to take 4 bytes, and we want to start here. 1, 2, 3, 4, 5. Let's do 5, just because it's going to be easier to write in the diagram. So let's say we want to take these 5 bytes, and the distance back would be 1, 2, 3, 4, 5, 6, 7. So the dist is 7 here, right? So dist equals 7, because this is how far back we're going to go. And s member out count minus dist. So the first time we start here, because this is this spot x, let's make it underscore. This is no memory yet. This is So out count is also the seek position, right? So empty memory slot. So out CNT is also a seek position. So it's important to remember that out count here is also a seek position, because that can be kind of confusing if you just think of count as the number of bytes in the output buffer. You also need to remember that out count is also being used as a seek position. So from here, right, we go from out count and we go this distance back and we get this first byte that we want to copy. And we do this len number of times, right? So that we had that len minus minus in the top of the loop. And every time, for every len minus minus, we do out count plus plus. And that out count plus plus is going to increment the value of this formula by 1. So that means the first iteration we're going to get this value, the next iteration we get this, we get that, we get that, we get that, and we do it len number of times. So if we look at the code again, so that's line 500. So I'm just making a note that this is line 500. Okay. So right here we can see the len minus minus, and while len minus minus, so that's a post increment, and it's going to be falsy or false once it hits 0. So let's say that len starts out as 1. Then the first time we hit this, len is going to be equal to 1, and we're going to do the loop. And then the value is used, and then it is decremented. And then the next time we get here, the value is 0. So we use the value 0, which means we won't do the loop next time. And then len will now be negative 1, which is a bogus value, but it doesn't matter because we're no longer in the loop. So this is just a thing to say loop len number of times. So this is a very concise way to say loop len number of times. And I can see where these people are coming from, where if you're very familiar with these types of, I think it's called an idiom. If you're very familiar with these types of idioms, then being terse like this is actually clearer than a for loop, I guess. But anyways, so that makes sense to me how they're copying this strip here, and in this case, example len equals 5. So in our example, len equals 5 because it's right here. And actually, we should probably do it like if I'm going to write this diagram. If it's going to be a diagram, you might as well do this. What the hell am I doing here? So, right? Okay. So we have a little diagram to kind of explain how that logic works. Stepping through the logic might also help, but I think it's important to be able to step through in your head. Because debugging can be very hard, and if you can actually debug it in your head rather than have to do it in a debugger, it's just a lot simpler for you. Okay, so this way to copy len number of bytes from a certain position backwards. So we're going to copy len number of bytes from a certain position backwards. That makes sense to me now. So I'm going to look at this else statement here. Else, that would be the end of block code, I believe. So let's keep this lined up. Yeah, if symbol less than 0, And then no, we're not in that. We're not at that level, are we? No, it's oh no, that's not what I'm looking at. So this else, so that else right there is if we're not doing any copying of data because an output buffer doesn't exist, then we just want to tally how many bytes would have been written because we're just trying to figure the size of the uncompressed data. So line 504, we're just trying to figure out the size of the uncompressed data without doing any copying of the data. And everything in here is, if we actually have an output buffer, right here, then we're going to actually copy the bytes. Otherwise, we're just going to take a running total right here. And then while symbol not equal to 256, right? And 256 was the end of block symbol, which we already knew. But that while loop... Okay, so this function is basically just a while loop. Like the... like all of the actual... right, we have data, but like all of the actions within the codes function here are within this are within the do loop here. So symbol less than 0, less than 256, symbol greater than 256, and we don't handle 256 because 256 is the end of block symbol, and it looks like it is meant to be hit while already inside of the loop, while already having made a decision. So that makes sense to me so far. And on line 508, done with a valid fixed or dynamic block, and will return 0, 0 indicating that there is no problem. Okay, so that makes sense to me. I've read through codes. So this is function codes in Puff.c. And I'm going to stop this video so we can read the next function. And then hopefully after reading all of these functions, I will be able to start writing my own deflate method. But chances are that I won't have remembered everything. Like, I've figured it all out and made sure that I've understood all the code I've read, but I'm not sure how much of that I'm actually going to how much of that is going to persist in my memory over a long period of time. I wish I had a photographic memory, but I don't. So we just gotta keep on crunching away at it, and hopefully we'll understand it. And hopefully, after we do this and figure it out the first time, it won't matter how long it took us because it'll just be there, right? Okay. So that's the end of the codes function. We are now looking at the fixed function within Puff.c. We're going to read the comment first, and then we will go into the body of the function. So on lines 512 to 535, we have a large block comment. Process a fixed codes block. Format notes. This block type can be useful for compressing small amounts of data for which the size of the code descriptions is a... Sorry. Let me say that again. Format notes. This block type can be useful for compressing small amounts of data for which the size of the code descriptions in a dynamic block exceeds the benefit of custom codes for that block. For fixed codes, no bits are spent on code descriptions. Instead, the code lengths for literal/length codes and distance codes are fixed. The specific lengths for each symbol can be seen in the for loops below. Okay, next paragraph of the block comment. The literal/length code is incomplete, but has two symbols that are invalid and should result in an error if received. This cannot be implemented simply as an incomplete code, since those two symbols are in the middle of the code. They are 8 bits long, and the longest literal/length code is 9 bits. Therefore, the code must be constructed with those symbols, and the invalid symbols must be detected after decoding. So, I'm going to tell you right now, most of that just went over my head. I'll read it one more time, and then if I don't really know what they're saying, I'll just kind of keep on going. The literal/length code is complete, but has 2 symbols that are invalid and should result in an error if received. So I think when they say code, they don't mean like a single code. They mean a code as in like an alphabet, right? And that's where I'm getting kind of confused. If you think of code as a alphabet, or rather than, I would write it like codes instead of, but they're using the verbiage as code as in like a collection of things rather than a single code, right? And if you think of it like that, then that sentence actually makes sense. That they're saying that there is this set of codes that is complete, but there are 2 symbols within this codes that are invalid and should result in an error if received. Yeah, so you really just have to read code as a collection of things. Symbol would be a single element within a code. This cannot be implemented simply as an incomplete code since those 2 symbols are in the middle of the code. So I'm not sure why this is a thing. It can't be an incomplete code, right? And code is, once again, like an alphabet. They're saying you can't just have it as an incomplete code because you can't just truncate it because it's the missing data is in the middle, is what they're saying. Okay. So it'd be one thing if you were missing, like if let's say our code is the alphabet, A, B, C, blah, blah, blah. Well, if we're missing Z, then it's at the end, so we can just truncate it, and that would be an incomplete code, right? If we had A to W, but XYZ, we're missing XYZ, that could be implemented as an incomplete code because the symbols are missing from the end. But if we remove like R, which is like in the middle of the alphabet, but we want to keep like Z, well, we can't implement that as an incomplete code because the symbol we just took out was in the middle of our code being the alphabet. Okay, so that makes sense to me now. They are 8 bits long, and the longest literal/length, I'm not sure why there's a backslash here. The longest literal/length code is 9 bits. They are 8 bits long, and the longest literal/length code is 9 bits. So I don't understand that. They're saying they're 8 bits long, but the longest one is 9 bits, is what I'm reading. Unless I think that they must be referring to the symbols, 8 bits long, which makes sense because the deflate algorithm is deflating data in byte format. It's deflating bytes of data. It works on a binary stream, but the end result is deflating chunks of bytes. So 8 bits long, the they definitely is probably talking about, the they is definitely talking about the symbols. That makes sense. So the symbols are 8 bits long, and the longest literal/length code is 9 bits. Okay, that makes more sense. Therefore, the code must be constructed with those symbols, and the invalid symbols must be detected after decoding. Okay, fine. So it's just saying, because if we're missing some codes if we're missing some symbols within the middle of our code, we're just going to have to detect those after the fact, because of the way things work. And that's kind of how I'm interpreting that. 531 to 535, we have another comment. The fixed distance codes also have 2 invalid symbols that should result in an error if received. Since all of the distance codes are the same length, this can be implemented as an incomplete code. Okay, so maybe I didn't interpret that previous paragraph correctly. Then the invalid codes are detected while decoding. Okay, so I don't quite understand that, but we need to just read the code, and we've kind of primed our memory for understanding the code, so let's just read the function now. Line 536. Local int fixed struct state pointer s. Static int virgin equals 1. Static short len count max bits plus 1. Comma len sim fix L codes. Static short dist count max bits plus 1. Comma dist sim max decodes. Static struct Huffman len code dist code. So that's interesting. So they are declaring the related variables on the same line. So the len count and the len sim are declared on the same line, and then dist count and dist sim same line, and the len code and dist code Huffmans are on the same line. That's interesting because I believe in other functions we aren't doing that. I'm looking at some of the other functions to see if this is a style thing that construct okay, so looking at the other code, on the other code where they're declaring arrays that are related, is here in the codes function, but obviously they can't declare both of lens and lext on the same line because they're initializing it when they declare it, and right, there's a lot of stuff here. So even if they wanted to concisely declare lens and lext on the same line, it wouldn't make sense, right? Because you'd have a really long line, and you could say omit this semicolon and use comma instead, and then get rid of this right here. But that would be confusing to read. Okay, so I just wanted to kind of like understand. Okay, yeah. So I just was curious as to why it was done in this style, but I don't see anywhere where this style could be used elsewhere. I tend not to like to do this because when I'm skimming through code really fast, like I won't see this and I won't see this. But I see why they did it like this, so you can associate these two and these two together because they're related. They're like they're I guess they're kind of like paired arrays, even though they have different lengths here. And that also might help to declare them on the same line because these do have the same length. I guess actually we have like two-way pairings. We're paired this way, and then we're also paired up and down. Like this is paired with this, and then this is kind of paired with this in a way. I don't know. Let's just keep going. So len code and dist code are Huffman structs. Dist count and dist symbol are length code and distance code. Lengths and symbols. No, this is frequency. This is the frequency table, and this is the symbol table, and this is frequency table, symbol table. Yeah. And length and distance, right? So LZ77 compression. I think that's the first one that does this. That like, well, maybe that was LZW, but right, the essence of the algorithm, right, is that you have a length and distance, right? A number of characters to take, and then a distance backwards to look. All right, let's just keep on reading this. So 543. Build fixed Huffman tables if first call may not be thread safe. Okay. So static. Oh, great. Yeah, these are all static, right? So the static means in the case where static is in a function, it means that these allocations here only happen the first time the function is ran. It's kind of like these are like function private variables. They can't be accessed from outside of the function. So static has a lot of meanings. Okay. So most of this code in this function is just run once code, because 572 is where this ends, and then the only code that's always executed is codes, the state struct, and referencing the len code and dist code, which are declared within oh, hold on. Len count dist. So this looks like a one-time use thing. Because we're gonna like use it. We're gonna use it here only for one time, and then all of this stuff never gets used ever again. And len code and dist code are just where are len code and dist code coming from? We have state right here. Oh, len code and dist code are these Huffman structs. Okay, so it looks like we are these look like maybe they're helper variables to create len code and dist code. And so this is always going to be used when we rerun this function. And len code and dist code are going to be like assembled within this virgin block. And then every other time the function runs, all is it going to do is it's going to call codes with the state struct and then a reference to len code and dist code Huffman structs, which are going to be created within this function. And they're kind of like lazily created. They're lazily initialized. Or that's what I would call this right here. This is called lazy initialization. Okay, so on line 543, the comment is build fixed Huffman tables if first call, may not be thread safe. Okay, we read that before. 544, if virgin. So let's look in the block. We have int symbol short lengths fix L codes. So the fixed number, the number of fixed length codes. Construct len code and dist code. Lencode.count equals lencount, lencode.symbol equals lensim, distcode.count equals distcount, distcode.symbol equals distsim. So we're just doing a copy over, okay? So nothing fancy there. Okay, 554 to 563, we have a comment on the block, which says literal/length table. And then 565 to 568 looks like the distance table from the comment at the top. So let's look at literal/length table. For symbol equals 0, symbol less than 144, symbol plus plus. So why are there 144 symbols? I don't know. That could be just part of the spec. 144, that seems just kind of lengths symbol. Yeah, 144, that's just really weird. Well, it's the length table, so 144 might be the maximum backward amount for deflate. So if we look at the deflate spec, and let's just take a look really quick and see if we look for the number 144, I bet we'll find something. Okay, so in the spec, I see compression with fixed Huffman codes, B type equals 0, 1. And that is what we're doing. We're in the fixed function. And I do see 144 right here, 144 to 255. But this isn't what we'll be using because 144, right, we start counting at 0. So we're actually looking for 143. And so this, bits 8, I was talking about 8 bits in their codes. So this through that is the fixed Huffman code range. The Huffman codes for the 2 alphabets are fixed and are not represented explicitly in the data. The Huffman code lengths for literal/length alphabet are. Okay? And then so we have these different tables, 144 to 255, 256, 279, 280 to 287. And if we look at this code again, if the symbol equals 0, for symbol equals 0, symbol less than 144, symbol plus plus. Okay. So it's just saying that the length is 8 bits, right? And right, because this is an 8-bit symbol. Okay, that makes sense. And why does my... Okay, for symbol less than 256. So this is... this is quite terse code, but basically what it's saying is we're going to pick up where we left off. And this is 144 to 256. If we look at here, 144 to 255. Oh, sorry. So this is 144 to 255. And we see 144 to 255, and that's 9 bits. And if we look here, we see 9 bits, right? And okay, so then over here we have, we're gonna pick up where we're once again picking up where we left off again. All right, this is very terse code. So less than 256, so we're gonna go 256 to 279 here. If you look at here, 256 to 279, that's 7 bits. And we're just gonna put 7 for 7 bits. And then we go back to 8. Why is that? I don't know. That's what the spec says. That's how you got to do it. 280 to 287. Does that make sense? Yeah, here's the 280. So 280 to fix L codes. And fix L codes must be 287 or 288, right? Because we start counting at 0. So if we go up here, we'll probably find that in fix L codes at the top. Yeah, so fix L codes, we see a 288 right there. Okay, so that makes sense. So let's read that spec again. So I get that it's kind of creating the histogram that's going to be used in creating the codes. The Huffman codes for the two alphabets are fixed and are not represented explicitly in the data. The Huffman code lengths for the literal/length alphabet are. Yeah, I mean, I think I know as much as I can from reading that. Let's go back here. What is this? So construct len code and lengths fix L codes. Okay. So the construct function is going to construct the Huffman codes from the frequency table that we just created. So and len code. Yeah, len code is the len code is the Huffman struct. Yeah, so we are passing the Huffman struct by reference, and we're taking our frequency table and the max number of codes, and we're using that to, I believe, construct this Huffman object, which we've already looked at that function, but let's review that really quick and look at the construct function, make sure that I understand that correctly. So construct and construct the tables required to decode those codes, right? Okay. And inside the Huffman struct, do we have the Huffman struct, I believe, is what we're actually populating here. And let's look at where is h? Yeah, because we have the tables in here, h.count. And h symbol, right? And then h symbol here as well. Yeah, so the Huffman struct is basically everything we need to decode Huffman encoded data. Okay, so I'm happy with understanding this call right here. And we looked at the spec, RFC 1951, for what these numbers mean here. Okay, so the distance table. It looks like the same deal, but symbol 0, symbol less than max codes, symbol plus plus, lengths, symbol equal 5. So why is the distance table just all the symbols in the distance table are always 5 bits, is what they're saying. And do we have another table like this really close? I mean, we could try to, look for a 5, but that's going to be much harder than just looking for, 144. Yeah, so right here I see 5 bits hdist, number of distance codes -1, 5 bits hlit, number of literal / length codes. Okay, so length and distance right here. Preset dictionary might discard part of the output stream. A distance can refer to that part of the output stream anyway. Also note that the reference string may overlap the current position. For example, the last 2 bytes decoded have the values x and y. The string may reference with length equals 5. Okay, no, that's a length. That's not the number of bits. But yeah, so I think that the distance back is always encoded as 5 bits from looking at from looking at the code. From looking at the code, I mean, that's what the code is saying. It's saying that all of the... I don't know why I can't see a similar table. But yeah, always 5 bits for the distance or the lengths. Well, hold on here. Let me make sure... 0 to whatever, length symbol. Okay, so that's kind of confusing. So they're accessing the same array, and they're accessing the same symbols, because like symbol 0 to 144 here. So it almost looks like they're taking this lengths that we built, and they are modifying it. They're modifying it, so they're reusing the lengths, right? Yeah, they're reusing lengths here, right? And they've just modified it so that 0 to max decodes is getting set to length of 5. So if we go look at, were we able to find 144 last time? Yeah, we were. Yeah, I'm not sure what that's about. But it does appear that we are kind of like, it does appear now that, right, I thought that this was an isolated chunk of code, and that this was another isolated chunk of code doing a similar thing, but all the symbols were just 5 bits. But now that I see that we are reusing lengths, that's not the case. Unless we only go up to max decodes, right? Yeah, because we have fix L codes right here. And lengths fix L codes. And then we have max decodes here, max decodes. So I think what we're doing is we are reusing lengths. All the symbols definitely are 5 bits, but then all of the... but we're not worrying about having junk data in our array, right? We're just going to reuse the same lengths array, but we're only going to read up to max decodes. Alright, so now I think I understand what they're doing. Why they're doing it, I'm not completely clear on it, but I cannot derive the why from just reading the code. As long as I understand exactly what the code is doing, that is enough for me for the reading part. Other levels of understanding are going to take some supplemental reading. So do this just once. That makes sense. Virgin equals 0, so this block is only executed once. And then those codes that we constructed, len code and distcode, that we constructed using the construct function up here, we are going to use those Huffman structs to do the codes function on the state object. And this is for decoding fixed Huffman codes. Process a fixed codes block. Yeah, okay. So I get what's going on there. The whys of some of the things that are going on, I'm not quite sure. But I think I understand enough of the fixed function that I can stop reading that and get on to the next function in Puff.c. We are looking at the dynamic function of Puff.c. The first thing we want to do is read the block comment at the top of the function, spanning a lot of lines here. Lines 578 to 664. We have a big block comment on top of the function dynamic, and we're going to read what that is all about. Okay. Process a dynamic codes block. Format note. A dynamic block starts with the description of the literal/length and distance codes for that block. New dynamic blocks allow the compressor to rapidly adapt to changing data with new codes optimized for that data. The codes used by the deflate format are canonical, which means that the actual bits of the codes are generated in an unambiguous way simply from the number of bits in each code. Therefore, the code descriptions are simply a list of code lengths for each symbol. The code lengths are stored in order for the symbol, so lengths are provided for each of the literal/length symbols and for each of the distance symbols. If a symbol is not used in the block, this is represented by a 0 as the code length. This does not mean a 0-length code, but rather that no code should be created for this symbol. There is no way in the deflate format to represent a 0-length code. The maximum number of bits in a code is 15, so the possible lengths for any code are 1:15. The fact that a length of 0 is not permitted for a code has an interesting consequence. Normally, if only one symbol is used for a given code, then in fact that code could be represented with 0 bits. However, in deflate, that code has to be at least 1 bit. So, for example, if only a single distance base symbol appears in a block, then it will be represented by a single code of length 1, in particular, 1 0-bit. This is an incomplete code, since if a 1 bit is received, it has no meaning, and should result in an error. So, incomplete distance codes of one symbol should be permitted, and the receipt of invalid codes should be handled. It is also possible to have a single literal/length code, but that code must be the end of block code, since every dynamic block has one. This is not the most efficient way to create an empty block. An empty fixed block is fewer bits, but it is allowed by the format. So incomplete literal/length codes of one symbol should also be permitted. If there are only literal codes and no lengths, then there are no distance codes. This is represented by one distance code with 0 bits. The list of up to 286 length/literal lengths and up to 30 distance lengths are themselves compressed using Huffman codes and run length encoding. In the list of code lengths, a 0 symbol means no code, a 1:15 symbol means that length, so it's literally that length, And the symbols 16, 17, and 18 are run length instructions. Each of 16, 17, and 18 are followed by extra bits to define the length of the run. 16 copies the last length 3 to 6 times, 17 represents 3 to 10 zero lengths, and 18 represents 11 to 138 zero lengths. Unused symbols are common, hence the special coding for zero lengths. The symbols for ... 18 are Huffman coded, and so that code must be described first. This is simply a sequence of up to 19 3-bit values representing no code 0, or the code length for that symbol 1 ... 7. A dynamic block starts with 3 fixed size counts, from which is computed the number of literal/length code lengths, the number of distance code lengths, and the number of code lengths, okay, you come up with a better name, in the code description. For the literal/length and distance codes, lengths after those provided are considered 0, i.e. no code. The code length code lengths are received in a permuted order. See the order open bracket, close bracket, array below. To make a short code length list more likely. As it turns out, very short and very long codes are less likely to be seen in a dynamic code description, hence what may appear initially to be As it turns out, very short and very long codes are less likely to be seen in a dynamic code description, hence what may appear initially to be a peculiar ordering. So I think they're talking about the hard coding of those arrays. Given the number of literal/length code lengths, nlen, and distance code lengths, ndist, then they are treated as one long list of nlen plus ndist code lengths. Therefore, run length coding can and often does cross the boundary between the two sets of lengths. So, to summarize, the code description at the start of a dynamic block is 3 counts for the number of code lengths for the literal/length codes and distance codes, and the code length codes. This is followed by the code lengths, 3 bits each. This is used to construct the code length code, which is used to read the remainder of the lengths. Then the literal/length code lengths and distance lengths are read as a single set of lengths using the code length codes. Codes are constructed from the resulting 2 sets of lengths, and then finally you can start decoding actual compressed data in the block. For reference, a typical size for the code description in a dynamic block is around 80 bytes. Okay, so I'm going to say I didn't comprehend.
Jamie,
What?
when you get a chance, will you help me lift something?
Okay.
Thanks.
Okay. So line 665, local int dynamic, and within there it takes one parameter, struct state pointer s, open curly brace to open up the function on line 666. We have a lot of variable declarations here, spanning 667 to 675. So we have int nlen, ndist, encode, number of lengths in descriptor, int index of lengths, int construct, return value. Not sure. Oh, the return value of construct is what they're saying. ERR probably is some type of error code. 670 short lengths max codes. Descriptor code lengths. 671 short len count max bits plus 1. Len sim max L codes. Len code memory. 672 short dist count max bits plus 1. Dist sim max decodes dist code memory. 673 struct Huffman len code discode length and distance codes. 674 static const short order 19 equals permutation of code length codes. And we have an array here that has the numbers 16, 17, 18, 0, 8, 7, 9, 6, 10, 5, 11, 4, 12, 3, 13, 2, 14, 1, 15. And I believe that is something that is encoded into the spec. I'm not sure how we would find that. We could try to... we could try to take a piece of that and see if we can find it, but to see if it's in there verbatim like that, yeah, that's probably very unlikely. We could try, I don't know, we could try the number 17. Yeah, I don't think we're gonna... Well, this is the only place where we have the number 17 in the spec. 16, 17, 18, 0. Yeah, I don't know where they are getting... I don't know where this array is coming from. And I don't see it in here anywhere. What? Well done. 16, 17, 18, 0. 16, 17, 18, 0, 8, 7. 8, 7, yeah. Okay, well, what the hell? Did I not put the number 17 in here? Okay, so that is kind of confusing because y is... It's gonna find this, it found this, but there's obviously a 17 right here. So there's a 17... There's a 17 right here, and my control F is not picking up that 17. Is this, like... Is this Unicode or something? Is it... What's the deal here? So, obviously you have a break there, which, means that if we search for 16, 17, 18, 0, we wouldn't be able to find it. But that 17 doesn't look like anything special. So let's say we copy this 17 directly, and then we search for 17. What the hell? Okay, now we're getting more results. But when I typed it, if I type 17, I don't know what that's about. Because there it is, obviously. And when I was over here, I typed 17, and maybe there was a space in 17. Okay, that would explain it. And then I went over here to delete it. Yeah, I don't know. But that array in the spec looks like, and it's 14.115 at the end. 14.115, yeah, that looks like a match. So HC len plus 4 times 3 bits, code lengths for the code length alphabet given just above in the order. Okay. So this is, what page of the spec is this? This is page 14. So we know that we might want to make a note, that, page 14 of spec, 14. So make a note that this is page 14 of the deflate spec. We can just copy that over here. And then we'll just make a note that that is for trying to figure out this function right here. So we'll just keep that in our notes of where that array is coming from. So we did find the source in the spec. It's just important that when we see like random magic numbers popping up, we want to know where they're from. It's good that we assume that this Puff.c works, but we also want to cross-check it against the spec. Okay, so we know where this array is coming from right here, and permutation of code length codes, order 19. Do we want to read that a little bit more? H. So HC len plus 4 times 3 bits code lengths for the code length alphabet given just above in the order. These code lengths are interpreted as 3-bit integers 0 to 7 as above. A code length of 0 means the corresponding symbol, literal / length, or distance code length is not used. Yeah, I don't know. Let's just keep reading the code here. So construct len code and dist code. Okay, len code plus count equals len count. Len code dot symbol equals len sim. Dist code dot count equals dist count. Dist code dot symbol equals dist sim. So a straightforward copying of values that are being declared in this function. Yeah, len count. Oh, these are not values. These are pointers to arrays that have been declared on the stack. And the Huffman has also been declared on the stack, so that's okay. I usually get kind of worried when I see referencing when you put array addresses into a struct, and those array addresses are to arrays that are declared on the stack. That just makes me worry that the memory address is going to get invalidated, and you're going to get a memory stomp, and that's harder to find than a seg fault. So, but no, I mean, since the Huffman len code and dist code, since those Huffman objects are also allocated on the stack, then we don't have to worry about assigning these pointers to things that are also allocated on the stack. That's perfectly fine. Okay, so going down a little bit further, we have 683 get number of lengths in each table, check length. So nlen equals bits. We're getting 5 bits plus 257. 685 ndist equals bits. We're getting 5 bits. We're adding 1. 686 encode. We're getting bits. We're getting 4 bits, and we're adding 4 to it. So that has to do something with how the data is packed, how the data is packed into the binary, and we can probably find something close here. So we actually have h lit 257, right? We're adding 257, h dist plus 1, and the 257 and 1, here's our 257, here's our plus 1, and then there's encode, and that's plus 4. And then, oh yeah, so HC len plus 4 bits. Okay. So we kind of see where that's coming from. It's weird that this one is last, but it's mentioned first in the spec. Where are we getting that specific ordering from? If we look for just 4 for a second, Control F, and we look for the number 4. Okay, so I'm going to guess it is right here is where this is coming from. Yeah, minus 257, minus 1, minus 4. So it's saying it's these 5 bits, and the value of it is this value minus 257. 5 bits is this value minus 1. 4 bits is this value minus 4. And so to reconstitute those values, we just have to add these values to get back just this, right? Like this, with no operation appended to it, we got to cancel those out. So that's why we're seeing negative, 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 257, 1, and 4. Oh, sorry, probably can't see that. So right here, 5 bits to get this data, but it's that data minus 257. 5 bits to get this data, and it's a minus 1. And then 4 bits to get this data, and it's a minus 4. So we got to cancel out 257, 1, and 4. So we're going to see 257, 1, and 4 in that order. And so we're going to take this, and this is page 13 of the spec. We're just going to put that in our notes. So page 13, deflate spec. And so now that we know that, we know where 257, 1, and 4, right? This 257, 1, and 4 is kind of reconstituting these values that we can see in the spec right here. So HLIT, HDIST, HCLen. Are they using the same exact variable names as well? Not quite. NLen, NDIST, encode. Yeah, not exactly the same variable names, but that I'm confident that that is what those variables stand for. Literal, distance, and code length codes. Literal, distance, and code length codes. So this is probably like n number of bytes, or n number of bits for the length, n number of bits for the distance, n number of bits for the length of the length code. Okay, so if nlen is greater than max L codes, or ndist is greater than max dist codes, then return -3 bad counts. So we just have corrupted data, and we're going to return -3. Okay, so on 690, we have read code length code, read code length code lengths, really, missing lengths are 0. For index equals 0, index less than n code, index plus plus, lengths order index equals bits 3, and then we're going to continue where we left off with index and all the way to 18. And then we have semicolon index less than 19, index plus plus, lengths order index equals 0. Okay. So order is the way the data is packed, right? So if we look at order right here, order was this thing, permutation of code length codes. Okay. So looking at order, we know that this is just like a lookup table for the code lengths. And we're using order in both of these here. So order, we're going to put in an index, right? So we're going to just go through, and it's just going to give us a certain length out. And bits equals 3. So that must mean that for the values up to n code, in n code is, so n code itself is dynamic, number of codes. But that means that pretty much all these values can be represented by 3 bits. Does that make sense? I thought 3 set bits would be a 7, not a 15. So really quick, let me check in. So 0, B, 1, 1, 1, to decimal is 7. Okay. So with 3 bits, we can only get the value 7. So does that? But the first value is 16 here. So let's take a closer look at here. Well, hold on. Lengths, order, index. So oh, you know what? It looks like what we're doing is lengths and lengths. Is this just the way the data is packed? This is the way the data is packed, but we want to sort this back into the correct order. And that's why we have this lookup like this. So lengths, order, index. Yeah, I think so. So if we look at these are, if we like, if we could take this really quick and, let's see if I can use this on it. No, that did not work. So if we take all these values really quick and do I have a unvarg but with commas? So I don't have so really quick, what we could do is just go, we take this like that, copy, Control F. Oh, that's not going to work. Well, actually, maybe. If we look for comma, and then we allow extended sequences, and then we just replace it with space or just a new line. And then we go find next, and we do a replace. There we go. Okay. So now we have all of these numbers in the order. Or Shift Tab. Okay, so we have all these numbers in the order that they are within the array. There's not 2 1s at the end, though, are there? Where did I get 2 1s? 14, 1, 15. Oh, this should be a 15. So we must have chopped that off. So really quick, looking at this, I'm fairly certain that matches. So what I want to do is I want to take this really quick, and I just want to make a copy, and I'm going to lexigraphically sort this. So file, edit, line operations, sort lines lexigraphically ascending. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so it's all there. So what's going on? So my guess is the Huffman tables that are encoded with the data are themselves encoded using Huffman codes, which that's kind of confusing, but I believe something about the compression just says that, you know, if we store the data like in this order, that it will be easier to compress for whatever reason. So they did this. So, and this is the order, right? So this is the order in which these different lengths are stored in the data when we're looking, when we're fetching 3 bits at a time. 3 bits for this one, 3 bits for this, 3 bits for that, 3 bits for the value of this, 3 bits for the value of this, 3 bits for the value for that, right? So then in here, we're just trying to extract all of the lengths in this, and we're trying to create this lookup table, but we are kind of like it's kind of like random access as to, rather than populating every value sequentially, like it would be much easier if this was just index, right? And then we just got the current length in the array, but we're kind of like sparsely populating this array, or we're populating it in kind of a random, pseudo-random order dictated by the orders array, and just going through the binary data and 3 bits at a time. So these lengths here are represented by 3 bits, so the length can be 0 to 7. But the indices here are going to be 0 to 18, but those indices are going to be populated in this just random kind of order here. Okay, so that makes sense to me now. As far as why do we do this, and then what's the difference here? So it looks like from encode to 18, it's just always 0, and encode is like number of codes. Yeah, number of lengths in descriptor. Okay, so we're just saying that, so I'm gonna guess, maybe that's their way of, if there's no data, we're just going to put a 0. So if the lookup table, if we've put a value in here and it doesn't have any meaningful information in it, it's like we don't have a symbol for that value or something like that, then we just put a 0. Something like that. I'm not quite exactly sure. Okay, so from there, let's look at this. Okay, so build Huffman table for code length codes. Use len code temporarily. So air equals construct len code lengths and 19. And that's going to construct our Huffman object for len code. And lengths is the thing we just filled out here. So that's our frequency table. That is our frequency table constructed in the binary. That's what we're fetching from here. And if the error is not equal to 0, then we have some type of problem. Require complete code set here, and we will return -4, and that would be an error code. Okay, so read length / literal and distance code length tables. Okay. Index equals 0, while index is less than nlen plus ndist. Well, let me just read through this and try to make sense of it after I've read it. While index less than nlen plus ndistance. We're going to open up the while loop with a curly brace here, and now we're inside the body. Int symbol, decoded value, int len, last length to repeat. Symbol equals decode s and len code. Okay. And if symbol is less than 0, return symbol, invalid symbol, right, because it's negative. You can't have a negative byte value. Well, it could be something else besides a byte, but negative is invalid. If symbol is less than 16, lengths index ++ equals symbol. Okay, length in 0 ... 15, else repeat instruction. Less than 16. So it's like, I believe this would be the 17 or 18. If the symbol is greater than, if the symbol is 16 or greater, then it's a repeat instruction, like a run length encoding instruction here. Len equals 0, assume repeating zeros. If symbol equals 16, repeat last length 3 to 6 times. Okay. If index equals 0, return -5, no last length. Len equals lengths, index -1, last length, symbol equals 3 plus bits, S and 2. So we're getting 2 bits, and then we're reconstituting the value by adding 3 to it. I don't know why they're doing the 3 in the front like this, because earlier in the code they were adding at the end, weren't they? So if we look at, yeah, so up here, way up here in the code, right, it's bits, and then they're adding their offsets here to reconstitute the values. But down here, I feel like that's an inconsistency, because now it's, I mean, it's obviously not a big deal. But 3 plus, right, because it doesn't matter, addition doesn't matter what order you do things in. So I'm not sure why these offsets are being applied. Whatever, it doesn't really matter, but it's just interesting to see that that inconsistency, and wondering if it's just an inconsistency or if they have a reason for it. That's just what I want to know. Okay, repeat last length 3 to 6 times. If index equals 0, return -5, no last length. Len equals lengths, index -1, last length. Symbol equals, and then we're going to reconstitute a value that, it's a 2-bit value, so that would be a 0, a 1, a 2, or a 3. And then we're going to add 3 to it. And it says 3 to 6 times. So if you take 3 and you add 3 to it, you get 6, and 0 adding 3 to it, you get 3. So that gives us our 3 to 6 that we're looking at. So, okay. If symbol equals 17, repeat 3 to 10 times. Okay, so we get 3 bits, right? The maximum value for 3 bits is going to be 7. And if we add 3 to it, that's going to give us a 10. The minimum value here is, well, 3 bits that are all 0 is a 0 plus a 3, right? So that gives us our 3 to 10 times. And lastly, if else what? Like, I'm going to assume that this means, like, symbol equals 18. Yeah, the comment even says 18. Repeat. So I would rather be more explicit with that, but whatever. 18, repeat 0, 11 to 138 times. Okay, so to get 11 to 138, we have 7 bits. 7 to the power of 2. No, 2 to the power of 7, my bad. 2 to the power of 7, really quick, is 128. And 128 plus 11 is 139. But remember that we start counting at 0. So when you do 2 to the power of 7, it's not 128. You would want to subtract 1 to get 127, because the range is 0 to 127 right here. So 0 to 127, and then plus 11, that will give us 11 to 138. So, okay, so that makes sense. That is sensible. If index plus symbol greater than nlen plus ndist, too many lengths, return -6. Index plus symbol is greater than nlen plus dist. So the number of length codes plus the number of distance codes are all stored in the same array, I think. Yeah, the lengths array. And If the index plus the symbol is greater than this, then we're out of bounds of that array. Or we're out of bounds of some type of array. I'm not 100% on which array that is. Okay, while symbol minus minus, repeat last 0 symbol times. Repeat last or 0 symbol times. While symbol minus minus. And so that's if the symbol is a run length code, which within this block, that's what the symbol means. Oh, got you. So we're going to take that symbol that's 16 or 17 or 18, and where we are modifying it by gathering more bits, right? We're modifying it here. And after we've modified it by grabbing more bits, then we will repeat symbol number of times and repeat whatever we're repeating, right? So length index plus plus equals len, right? We're just going to repeat this value symbol number of times and put it into length. So I kind of understand what is going on here, but I'd be lying if I understood the exact purpose, because I don't have, even though I've read the spec, I haven't absorbed it all, unfortunately. Okay, so check for end of block code, there better be one. So if length 256 equals 0, return -9. So I know that 256 was used as the end of block code. And I guess it's stored in length. So if we do Control F for lengths really quick. So it looks like up here in this region, that we want the index to hit 256. And when it hits 256, we're expecting to set the value to 0. Okay. And where would that happen? So symbol less than 0, less than 16, length 0 to 15. So somewhere around here, we're expecting this to hit 256. We're expecting this to hit 256 at some point, and that this symbol is going to be 0 to hit, and that's going to signify the end of the block somehow. Yeah, I'm not sure exactly what that is all about, but let's keep going. But that's some way that they're kind of looking for the end of the block. End of block code. But that's weird that we're looking for a 0, that a 0 has been set. I thought we would be looking for a 256 that's set, because 256 is the symbol for the end of block. Unless lengths right here, is length somehow initialized to something non-zero? Like, do we fill it with something? So lengths, Control F, lengths. Okay, so we do kind of. Yeah, I don't quite know. Because first we're like filling. Yeah, I don't know. Because it looks like we're filling out lengths here, but then we're also filling out lengths here as well. Yeah, I don't know. Let's just keep going. So build Huffman table for literal/length codes. Error equals construct and len code lengths and len. If error and error less than 0 or and len not equal to len code.count 0 plus len code.count 1, return -7, incomplete code. Okay, only for single length 1 code. Okay. So incomplete codes are only allowed if you only have one value in your that you're encoding. So let's say you have a text file and the only symbol in it is A, right? Well, then your Huffman code can have the bit 0 for A, and the bit 1 doesn't stand for anything because you only have the symbol A, and therefore that would be an incomplete code, but that's the only allowed incomplete code, so that's what they're talking about in this comment here. So if error and error is less than 0, and nlen lencode.count 0, lencode.count 1. Yeah, I'm not sure if this is exact logic here. I don't know what that means. Count 0 and count 1. What's the information in there? What's the information in there and why are we adding them? I don't know. Let's just look at the next thing. I don't quite understand this, but I'm running out of time. I have to go. So let's just read the rest of this, and maybe I'll come back to it later. Otherwise, I'm just going to keep on reading through the rest of the functions later. Build Huffman table for distance codes. Error equals construct and dist code lengths plus add len. So I believe this is like the starting pointer for looking in here. Maybe, and then end dist. No, because this is the Huffman object lengths plus add len. This is some type of offset, and the number of dist codes. Well, hold on. Is dist code? Yeah, because the dist code is a Huffman object. So if you go all the way up to the top, dist code is a Huffman object. So I don't know why that offset is. I'm going to have to check the signature of the function again. Error and error. So this is the same exact thing as the previous one. Incomplete code, only okay for single length of 1 code. So whatever this logic is the same logic as this logic here. I just don't know what that logic is about. You know, I get that somehow it's checking for incomplete code, but I don't know how this reasoning is working here. Decode data until end of block code, so return codes S, and then we're going to take the len code and dist code Huffman tables to do the decoding. And so that's the end of the dynamic function, which uses dynamic Huffman codes. And I'm going to stop streaming there because I got to go. The last function is the externally available symbol puff, which we will be reading, and then we'll be done with Puff.c. So Puff has a large block comment above it, spanning lines 749 to 792, and we're going to read that first. Inflate source to dest on return. Dest len and source len are updated to the size of the uncompressed data and the size of the deflate data respectively. On success, the return value of puff is 0. If there is an error in the source data, i.e. it is not in the deflate format, then a negative value is returned. If there is not enough input available, or there is not enough output space, then a positive error is returned. In that case, destlen and sourcelen are not updated to facilitate retrying from the beginning with the provision of more input data or more output space. In the case of invalid inflate data, a negative error, the dest and source pointers are updated to facilitate the debugging of deflators. Puff also has a mode to determine the size of the uncompressed output with no output written. For this, dest must be unsigned char pointer cast 0, in other words, a void pointer. Null void pointer. No, sorry, I'm not a void pointer at all. A null pointer to unsigned char. In this case, the input value of pointer destlen is ignored, and on return, pointer destlen is set to the size of the uncompressed output. Okay. The return codes are 2. Available inflate data did not terminate. 1. Output space exhausted before completing inflate. 0. Successful inflate. -1. Invalid block type equals 3. -2. Stored block length did not match 1's complement. -3. Dynamic block code description too many length or distance codes. -4. Dynamic block code description code lengths code incomplete. -5. Dynamic block code description repeat lengths with no first length. -6. Dynamic block code description repeat more than specified lengths. -7. Dynamic block code description invalid literal/length code lengths. -8. Dynamic block code description invalid distance code lengths. -9. Dynamic block code description missing end of block code. -10. Invalid literal/length or distance code in fixed or dynamic block. -11. Distance is too far back in fixed or dynamic block. Format notes. 3 bits are read for each block to determine the kind of block and whether or not it is the last block. Then the block is decoded and the process repeated if it was not the last block. The leftover bits in the last byte of the deflate data after the last block, if it was a fixed or dynamic block, are undefined and have no expected values to check. Okay. So the signature, or well, it's not really a signature, it's technically a prototype, but the name of the function, the type of the function, and its parameters. That's what I'm going to go over now. 793 int puff open paren unsigned char pointer dest comma unsigned char int puff open paren unsigned char pointer dest comma unsigned long pointer destlen comma const unsigned char pointer source comma unsigned long pointer sourcelen close paren. And let's go over what each of those are. So we have dest, destlen, source, and sourcelen. Those are 4 parameters to puff. Dest, pointer to the destination pointer. Destlen, amount of output space. Source, pointer to source data pointer. And sourcelen, amount of input available. So let's go over that again. So I'm going to go over each parameter, but in a different way this time. So for int puff, the first parameter is unsigned char pointer dest, which is pointer to destination pointer. Second parameter, unsigned long pointer destlen, which is amount of output space. Third pointer, const unsigned char pointer source, which is pointer to source data pointer. And the fourth parameter, unsigned long pointer sourcelen, amount of input space available. Unsigned long pointer sourcelen, amount of input available. Okay, on 797, we open up the function with a open curly braces. And 798 to 800, we declare some variables. So struct state s, input output state. int last comma type. So last and type are declared on the same line, and they're both of type integer. And the comment is block information. Line 800, int error, or ERR, return value. Okay, let's scroll down here if we can. 802 to 805. Initialize output state. s.out equals dest. s.outlen equals dereference of destlen. Ignore if dest is nil. 805 s.outCount equals 0. So we're just it's just a basic copy over of some of the input parameters. That comment on 804 that says ignore if dest is nil means that when we dereference destlen, it's going to be complete garbage data if dest is nil. But in the interest of keeping things concise, I believe that they just always copy it over no matter what, even if they're not going to use it. Okay, so 807 to 812. Initialize output state. s.in equals source. s.inlen equals source len, and that's a dereference of source len. s.incnt incount equals 0. s.bitbuff equals 0. s.bitcount equals 0. And bitcount is bitcnt. Incount is incnt. Okay. So that's just a pretty straightforward copying over of some of the input parameters and then zeroing out some of the state that we are going to use. So 814 to 832, we have a chunk of logic. The comment on the top says return if bits or decode tries to read past available input, and otherwise process blocks until last block or error. So on 815, set jump s.env not equal to 0. If came back here via long jump. So I believe set jump is returning non-zero when it is I forgot exactly how set jump works, but set jump is a mechanism to mimic throw. So you don't have throw in C, so they use the set jump thing, which manipulates your stack pointer. So kind of a dirty hack. But if set jump is called under normal circumstances, it's going to return a non-zero number. I believe it returns 1. But if set jump was called because of an error via calling long jump first, long jump kind of jumps back to wherever set jump is originally called from. So if long jump was called, which is basically a throw, then set jump, this set jump command here, where are you? This set jump command right here is going to return non-zero if we got to set jump, the set jump call from long jump, and long jump is like a throw. And also the comment right here says if came back here via long jump. And then error equals 2, then skip do loop, return error. Okay, that's relatively straightforward if you know the idiomatic code for the usage of set jump. Otherwise, it might look a little bit confusing. Okay, so if it's not an error, then process blocks until last block or error. And we have a do loop, and the do loop is terminated if the condition not last ends up being true. So do while not last. Okay, so we have last equals bits, and the state object, and 1 bit. 1 if last block. Okay. And then type equals bits, and we'll take 2 bits. So block type 0 to 3 inclusive, and I believe 3 is an invalid block type. But since we're taking 2 bits, right, you can have the values 0, 1, 2, or 3. Okay, so I guess every time we look at a block, there's always a flag, a bit flag, telling us if it is the last block or not. Judging from looking at this code. Okay, sure. Then on 822, we have error equals type equals 0. And then a question mark. So there's like a ternary expression here. So error and type are both going to get assigned to the same value. Yeah, error equals type. But then type is... okay, so... we're going to set error and type equal to each other, but then we're going to do a comparison on type. But then down here it says if error not equal to 0. So, not sure of exactly what's going on with that. Not really a fan of this kind of, I don't know. Okay, so if type is equal to 0, then we're going to do the stored command with the state object. Otherwise, if type is equal to 1, we're going to do the fixed command with the state object. Otherwise, if type equals 2, we're going to do the dynamic function with the state object. Otherwise, we're returning -1. And if error not equal to 0. Okay, so... so what I don't get here is... oh, okay, so I see. So I was wrong about error equals, and this is the beginning of our ternary statement. So we're not actually setting type, we're just comparing type. And if it's 0, process stored, 1, process fixed, 2, process dynamic. And then all of these functions, if nothing bad happens, they're just going to return 0, and that's why if error not equal to 0 here. And then -1 here, type 3, invalid block type. Okay, so that all makes sense here. So these are different type of block types from what we read earlier. There's a stored block, a fixed block, and a dynamic block. I know this is fixed Huffman codes. I know this is dynamic Huffman codes. I don't know exactly what stored is. I know I read the function, but I do not remember. I guess we could go back up to the stored function and see what that is. So bits, we already know. We're just getting bits from our buffer. Stored is process a stored block. So what is a stored block? Yeah, I'm not sure what the difference between So we have a stored block. Yeah, I do not know what the difference between stored and fixed, and what was the other one, dynamic? Fixed. Process a fixed codes block. Process a dynamic codes block. So I think dynamic and fixed are for getting the Huffman codes, but stored is for getting the actual data. That's gonna be my guess. Probably need to read the spec again. Oh boy. Okay, so I get the basic idea of what's going on here. There's these different block types. Reading up on what these different block types mean, because I have a vague notion that fixed Huffman codes, dynamic Huffman codes, and probably the data that you're decoding, this data that you're going to decode using either the fixed Huffman codes or the dynamic Huffman codes that are stored along with the data that you need to decode, right? Because deflate is using the LZW compression method, but it also uses Huffman codes. So I'm going to guess that this stored block is Huffman encoded LZW encoded stuff, and then this is just Huffman encoded fixed Huffman codes, and this is Huffman encoded dynamic codes, something like that. Okay, so and then while not last. So where is this last getting set? Okay, that's just here, right? So if it's the last block, we still process it, and then that's why we're going to check at the end of the loop. Okay, so that is sensible enough. And then on 834, update lengths and return. So if error less than or equal to 0, dereference declen and set it equal to s.outCount. Dereference source len and set it equal to s.inCount. So less than or equal to 0. So that's kind of weird that that if it's negative, we still set it. I think it was because in the comment they mentioned if it's negative, we want to debug the deflator or something like that. So negative might be more indicative of an error in the actual source code rather than an error in the data. So let's look at this for a second. So if we look at the error codes again really quick. No, because invalid block type would be an error in the data, not an error on the programmer's end. So yeah, we can't say that negative is always indicative of a problem with the source code. Available. So it looks like 1 and 2 are less serious errors. They're saying, you didn't allocate enough memory for this to happen. Well, no, that's number 1 says that, but number 2 kind of says that your inflate data, the data that you're trying to inflate, got truncated. Okay. So at the very end, we're just going to return the error code, which could be 0 for everything went okay. Then on 840 we close off the function. So that's the puff function, and that is reading all of the source of Puff.c. So I'm done reading the source, but now I have to review the source and probably also find, review the spec, and what else do I gotta do? Probably have to look over the spec again, the deflate spec. Probably look at the Paco library, which also does deflate inflate, and see how those algorithms work. Since I don't 100% understand everything I've just read, and I don't know, just go from there. I think to get a PNG library, what I really need to do is focus on just deflate and inflate, and make some tests for the deflate and inflate, and make sure just deflate and inflate work before I worry about more of the PNG decoding. So it's going to sidetrack me a little bit, but I think I really need to isolate this algorithm and get it working before I try to plug it into a larger piece of code. So anyways, I'm done reading the Puff.c source code. And yeah, I don't know if this was useful for anyone, but I just want to make sure I have, documentation showing that, I'm actually doing something with my time,